Hello, and welcome back to day 2 of EBPF Summit 2022. Tracy, it's good to see you again. I'm glad you're back with me.
I don't have a choice. I think we're all somewhere between chocolate coma and chocolate active. So if I'm a little bit dancier than I was yesterday, it's chocolate.
Yeah, we went to the Lynch Chocolate Factory today as a team building event, and it was tremendous. I mean, you walk into the place and you're just overwhelmed by the smell of this chocolate everywhere. It's totally amazing. So we do have some slides to talk through here. Another little bit of housekeeping.
All right, let's go.
So this is our, welcome, like I said, welcome to day 2. Make sure you join our Slack, ebpf.io/Slack.
Who are you? You didn't tell them who you are, Duffy?
I did too. I'm Duffy.
Oh, I'm sorry. Well, I'm Tracy. I didn't tell you who I was. I'm Tracy if you didn't see me yesterday. I work at ISOVille. There we go. All right, I'm sorry, go on.
Yeah. There we go. All right. And just like yesterday, this event is being being guided by the COC. So be human, ask people questions. One of the best ways for you to show your appreciation for all of the great knowledge and great context and perspectives that everyone is sharing with us here at this event is to ask them questions and, throw some words in Slack and be great to each other, and then further, be kind, just like it says in the COC. If you have any questions about how that works, definitely check out the link, isogo.to/COC. And that is important. Tracy?
All right, so I talked about swag yesterday, but again, we want you all to be a part of this. Go to ebpf.io/swag, find all of the wonderful things that you can either purchase or download, like that beautiful Zoom background that's there. And if you don't necessarily want an EBPF Summit t-shirt, sticker, or, bag, you can go get a shirt. I got a different one on today, like this. So just join us. Grab something, at least the background, okay? Oh, I almost forgot. If you grab the background, actually, we can, I was going to say, just go to the next one. So you see how that very nice background, and if we go to the next slide, you'll see that wonderful Infill watch party that I was so in love with yesterday. You see how Infill gave us their setup for the live stream? What we want from you all is, if you're okay or if you're comfortable with it, this is a virtual event. Show us your watch party or how you're enjoying the live stream. And if you want to share that in the Slack, maybe throughout today's stream or during a break, you'll get to see your setup on the screen.
That would be awesome.
The other thing I want to talk about, and you all know how I feel about this, is bingo. Have you all been bee hunting? So if you didn't grab all the bees yesterday because you couldn't, that's why you're here today. Continue watching through the slides and see if you can continue grabbing all of the bees. We need some great bee hunters around here. And if you find all the bees, share your screenshot of all of your bees caught, and you just may win a prize.
And then later this evening, are we going to show them where everything was, or?
I don't know. We just may. I might be, my last name is Holmes. I just may give them the answer to the mystery.
All right.
All right.
So logistics-wise, the stream that you watched yesterday is still at that same location. If you wanted to rewatch some parts of it, it's at https://ebpf.io Summit 2022 Day 1. And today's episode, as you're watching it now, if you want to share that link or pull somebody into it, you can give them this link, ebpf.io Summit 2022 Day 2. And just like yesterday, the schedule, if you open up the Summit schedule website, you're going to notice there are 2 tabs, Wednesday and Thursday. So Thursday's schedule is in the second tab. When it first, so if you're looking for Thursday, just click over. You'll be able to see all of the uploaded slides in the schedule. So if you click on any of the events that are coming up, you'll be able to see any slides that were made available to us. And here in a couple days, you'll also be able to see the video recording of that talk. So that's a great way to get back to that content when you want to. We have, you remember yesterday we did the first of the 3 CTF challenges. We are going to be doing a live solve of challenge number 2. Myself and Liz will be hosting that right after that. I think it's the second break, but we'll be doing that later today. And then we also host Echo Office Hours every Friday on YouTube. And if you attend this coming Fridays, you're going to see a recording of us solving the third challenge. Well, I'm solving it, and Liz is, like giving me subtle hints and weird looks every so often. Like, no, that's not. I don't think that's going to work. It's probably this. But you'll get to see us kind of doing that, like on Friday during the regularly scheduled UK office hours. And yeah, if you want to try it, if you haven't had a chance to do it yet, you can still follow this link, isogo.to/CTF2022. It's just built. It's great. It's got a great story behind it. It's really a lot of fun. And if you have the answer, feel free to just paste that into the Slack. If you have the answer, I mean, if you see the flags, you can put the flag up in the Slack. And if you want to talk about the answer, if you want to discuss how you came to this conclusion, go to EBPF Summit CTF spoilers. Don't put any of that information in the Summit Slack. Just move that to the spoilers Slack. The agenda for today. We are starting off with the amazing Marga Mantarola, who has joined us to talk about buzzing across the EBPF landscape and into the Hive. And then we also have All Your Queues Are Belong to Us, Debugging and Mitigating a Kernel Bug with EBPF by Laurent Bonnel. And then understand that these first two are keynotes. So we will be asking your questions live. So it's really important that while the presentation is happening, that you ask any questions that you have of our lovely presenters live, so that we can get those asked for you as soon as their presentations are over. And then we move into the talks for EBPF security. We have 6 talks for them. And then we have 10 talks for EBPF programming and internal. Still lots to say about that stuff. So pretty exciting. And then this slide, I feel like there's something about this slide,
Don't know what you're talking about.
Something extra.
Have no clue what you're talking about. Yep, none.
No, that's it. So that's the last slide. So yes, and that's all we have. So Tracy, would you like to take us forward?
I will take us forward. The very first of all, like I gave you, look, I told you all ahead of time, chocolate coma or the absolute other extreme. We're somewhere in the middle. So today I am going to bring you your first keynote. As always, place your questions in the Slack. Keynote questions are selected and presented live. Today's first keynote is going to be buzzing across the EBPF landscape and into the Hive with Marga Mantarola.
Hi, I'm Marga Mantarola, Director of Engineering at Isovalent. I'm here today to share with you my excitement about EBPF, the current and future state of our Hive. I got into EBPF 2.5 years ago when my former colleague Alban, author of Inspector Gadget, asked for help in delivering an EBPF workshop for KubeCon. I'm a big believer in the fact that teaching is the best way to learn something, so I jumped into this opportunity. I learned what EBPF is, how it works, and what it can do. And my mind was blown. The ease with which I could get the information I needed and understand what was going on in the system was something else. Using EBPF allows us to get kernel-level results without needing to be a kernel hacker. One of the things that got me hooked was how I could write a short and simple BPF trace one-liner and get the exact information that I was looking for. And that's only one tool among many. Every year we get more new tools based on EBPF, solving different problems or different aspects of a problem. And then we don't need to learn a domain-specific language anymore. We can just use the tools as they are. You are watching this talk as part of the EBPF Summit, so you might already be familiar with some aspects of EBPF. EBPF makes the kernel programmable. It makes it easy for developers to dynamically create code that hooks into the kernel to enhance observability, networking, and security. But why has EBPF been so revolutionary? Why is it so much better than writing kernel modules? There are a bunch of reasons. The first one is safety. The verifier checks that the code we write is safe and runs in a sandboxed environment. With kernel modules, it's easy to do something wrong and cause a panic, or worse, who knows what crazy havoc we might create. With eBPF, our screw-ups are limited to the BPF program itself. Another important feature of eBPF is portability, particularly after the introduction of BTF, the BPF type format, which makes it possible to write BPF programs that work on any BTF-enabled kernel without having access to the kernel headers. This lets us ship pre-compiled BPF programs to any BTF-enabled kernel without having to recompile them, just as we could for normal applications, but not the case for kernel hackers writing kernel modules. And yet another important aspect is the language diversity. While we still use C for the BPF code itself, instrumentation can be done in other languages like Rust or Go, leading to better integration with the rest of our system. All of this has led to more and more tools getting released each year that make use of eBPF to dynamically program the running kernel and provide efficient networking, observability without instrumentation, effortless tracing, and real-time security. Now, I want to come clean with something. When we talk about eBPF, we usually mention that it allows programmers to code the features they need in the kernel today without waiting for these changes to be merged in the kernel, released, adopted by Linux distribution, and finally reach consumers 3 to 5 years later. And this is true. Using eBPF allows for faster iterations, letting eBPF developers have a role in what the kernel is doing instead of having to always wait for kernel developers to get those features out. However, one thing that is often left out of this explanation is that eBPF has also been evolving for many years. Since it first got added in 2013, there have been a lot, and I mean a lot, of changes that have enhanced what we can do with it. When looking at requirements of an eBPF tool, it is pretty common for it to say that it needs at least some specific kernel version to work properly, maybe 4.19 or 5.4 or some other version. Some tools try to keep compatibility with previous kernels by implementing some missing functionality in user space. But that means the same operation running in an OS with one kernel version can take a lot more CPU time in another version. Or some functionalities might just be disabled when the version isn't high enough. The good news is that by now the basic eBPF infrastructure has mostly been stabilized, and while there still is significant innovation going on at the low level, the kernels provided by the stable releases of common Linux distributions include BTF support and can be used by most eBPF tools. However, before trying out the latest and greatest, it still makes sense to check the requirements and verify that your current kernel version is supported. So what are these tools that I keep mentioning? There are quite a bunch already, and I'm sure the list will keep growing as time passes and more people come up with new ideas of how to take advantage of what eBPF has to offer. So let's now do a quick overview of the current state of the eBPF landscape. We can basically split the tools into 3 categories. One important group has to do with networking. We can do a lot of cool networking operations with eBPF, in particular by making use of the XDP or Express Data Path. XDP is a framework that allows us to process packets at high rates directly in the kernel instead of having to go to user space and back. The decision on whether to allow or reject a packet is done by an eBPF program running in the kernel, leading to much better performance. In this group, we have tools like Cilium, a networking solution for Kubernetes. Cilium has been using eBPF from the very beginning, providing a comprehensive and efficient networking layer. Operations like applying networking policies, mapping services to the IPs of the pods in that service, or connecting separate clusters with a shared virtual network can all be done very efficiently thanks to eBPF. Another well-known networking tool based on eBPF is Ktran. Ktran is a layer 4 load balancing library that can handle extremely high traffic in an efficient way. On top of these well-established applications, there are a few other emerging tools in the eBPF networking space, like LogCLB, an external load balancer for the edge, or Merbridge, a service mesh acceleration tool. Next, let's look at observability and tracing, which is the category with the most tools. eBPF allows our programs to hook into specific events, like the execution of a syscall or the return of a function, and provide visibility as to what's going on without needing to change the code of the program that we want to observe. This can let us monitor, profile, audit, or debug our programs without any additional instrumentation. One of the first tools developed for doing this is BPF Trace, which comes with its own domain-specific language. This allows us to write simple scripts or even one-liners to get the data that we need out of our system without needing to write or compile the eBPF code ourselves. And there's also kubectl trace, which uses the same DSL and applies it to Kubernetes clusters. Another scriptable tool is Pixie, which captures telemetry data in Kubernetes clusters. It comes with some pre-created metrics, and we can add our own as needed. It also includes its own UI to visualize the data that it captures. On top of these generic, scriptable tools, there are quite a bunch of specialized tools that have been designed to solve specific needs. For example, Pyroscope and Parka are tools created for continuous profiling, allowing us to find why things take longer than expected while our programs continue operating. And Wacky is a tool that provides interactive profiling and debugging, letting us interact with the source code while we profile it. The tool I mentioned at the beginning, Inspector Gadget, is another observability tool for Kubernetes. It comes with an array of easy-to-use gadgets that help trace, profile, snapshot, and generally gather information about what's going on inside Kubernetes clusters. The list goes on. There's also Hubble, which provides network observability for Cilium, Kepler, a Prometheus exported for energy-related metrics, the Apache Skywalking rover, a metrics collector for the Skywalking project, and others. The next step, after detecting that something is happening, is taking action. This is where the third broad category of tools, security, comes in. Tools in this group can either log, alert, or even block execution when certain events take place. The power that eBPF brings to these tools is that we can have our tools check for certain actions without having any internal knowledge of what the application is doing. In this group, we have tools like Falco that applies rules based on system calls executed on our machines and can trigger alerts when those rules are violated. Tracy, that captures events as they happen and can detect suspicious behavior, and Tetragon, that combines monitoring the system for specific events with runtime enforcement when the established rules aren't followed, as well as more domain-specific solutions like KubeArmor for container-based applications or Pulsar for Internet of Things applications. If you are looking to develop a new eBPF tool, the eBPF ecosystem also includes a number of projects that help with creating and managing these tools. You can access the power of eBPF from C, Go, Rust, Python, and Lua. The BCC project provides a toolkit for easily creating eBPF programs and integrating them into other applications. The Leaf project provides lifecycle management of eBPF applications, and the Bumblebee project provides a packaging format for distributing eBPF programs as containers. And there's even an eBPF for Windows project aimed at allowing developers to apply the same principles that created eBPF to the Windows kernel, including some shared APIs. As you can see, the eBPF ecosystem is becoming quite broad. I'm sure that a list like this will be significantly longer next year. If you want to learn more about any of the projects I mentioned, you can find a more extensive list of open source tools that use eBPF with links to websites with more information at ebpf.io/applications. And if you have developed an open source eBPF tool and it's not listed there, make sure you send a PR to the site adding your project so more people can learn about it. Now, before we close, I want to emphasize that our community is continuously growing. No matter where you are on your journey today, whether you are starting to try out some of these tools, you are developing one of them, or you're a kernel developer adding some cool new enhancements to eBPF, your contributions are welcome. A bright and exciting future is ahead of us, and your participation will make it even better. Thanks for watching, and I hope you enjoy another day of amazing eBPF talks at the summit.
I need you all to know, one, that was a great talk from Marga because Marga is awesome. But also, the very first thing I noticed about Marga before I even knew how to pronounce her last name was the blue hair. Like, I love the blue hair. So,
Thank you.
and I need you all to know the first time we spoke, we were supposed to have a 30-minute meeting and it ended up being like almost an hour. So I'm very happy that I get to like host her for her keynote. I'm very happy. So thank you for the talk, Margaret. We're going to bring in these questions and I'm going to try to slide in an extra one that we weren't prepped for. Is that okay? All right.
Sure. Yes.
All right. What's that first question that we have? Let's see.
It on the screen right now. It asks, what are your favorite eBPF tools?
Yeah, because I don't see it on the screen, but hopefully it'll pop up in a little bit. But yeah, what are your favorite eBPF tools?
Sure. Yeah. So I think I have to say for my favorite eBPF tools, my favorite tool, Vector Gadget. I worked on it over a year, and I think it's really great because it's super easy to use, and it has a bunch of really useful gadgets that can give you the information that you need, like right at your fingertips. Yeah, so that's my favorite tool. And of course, I'm working on Cilium, and I think Cilium is really awesome. All the different things that it can do. It has so many different features, so many things that it adding like more features. Like latest release had so many features. So yeah, it would be my two favorite eBPF tools.
Nice. All right, let's see what that second question is. We might be able to pop it up. If not, I'm going to ask it to you anyway. So I think the second question we have is, yes, I love the IR Programmer t-shirt. So, and then somebody followed up and said, I want to know where you got it. So let's do it this way. Where did you get it? And how have you liked coming into the company as like an engineering director and knowing that we're all spread like all over the place?
Right. Okay. So the t-shirt was a present for me from my nephew. He actually like did it himself. It was a Christmas present, and
Aww.
yeah, I really love that t-shirt because it's really cute, and also like it reminds me of like my family when I'm away from them. I live in Germany and my family in Argentina, and so it's also like a tie-in to my family. And answering your other question about coming into the director for Isovalent, it's been quite a ride. The team is growing. There's a lot of new things coming in, a new set of challenges for me. And being such a distributed team, like we are all over the world, it has, it's really exciting to bring people together from all over, all different countries, different cultures, and have everybody working together to build such an amazing product.
All right. And for our next one, so just for the viewers, it's not popping up for me, but apparently you all are seeing the questions that are popping up and Margaret can see them. So that works just fine. All right. So I think the third and the last question is why doesn't Cilium support older OSs, or does it need the new kernel tie-in to work?
Right. Yeah. So I to talk the different features require kernel version, but actually Cilium supports quite like very old operating systems, and this is something that we take into account when we like put out a new version, like which operating systems we are going to support. And Cilium right now supports like everything that is stable, everything that is like the stable, long-term support. So it's like quite a few OSs. But the answer to the why question is because sometimes there are features in eBPF that require new versions, but we do work very hard to support as many as possible while still keeping the features working.
Thank you. All right, so for the rest of the question, because I do see some popping up in the thread and popping up in the Slack, Margo will be around for a while to answer those questions for you. So thank you so much for joining me. And I am now going to pass things over to Duffy.
Awesome. All right. So our next keynote is going to be by Laurent, and he's going to be speaking about a pretty incredible story. I mean, when we talk about eBPF being able to, to be able to make changes in the way that the kernel operates dynamically so that we can fix things up, this story really highlights that in an incredible way. So I'm really looking forward to this. The talk is entitled, All Your Queues Are Belong to Us, Debugging and Mitigating a Kernel Bug with eBPF. Welcome, Laurent.
Hello, everyone. My name is Laurent Bernaille. I work at Datadog as a staff engineer, and today I'm going to share an interesting kernel issue we identified, debugged, and fixed using eBPF. So a few words about Datadog. We're an observability company. We have many customers, about 2,000 employees, and a lot of different integrations. But today we're not going to talk about the product, we're going to talk about the infrastructure behind the product, which consists of dozens of Kubernetes clusters and tens of thousands of hosts. We already use eBPF extensively at Datadog, both on the product side for observability purposes, because we use eBPF to instrument the host we monitor. And we also use eBPF for our infrastructure. We use it for container networking because we use Cilium everywhere. And we also use it for debugging using BPF Trace, for instance. The issue I'm going to discuss today started with the performance regression. So two teams reached out to us telling that they were having issues with networking on a few clusters. Symptoms were packet drops and retransmits, which impacted throughput and latency. And as a consequence, they had to create more processing pods, and of course, it was more expensive. What was interesting is that only some clusters were impacted. The old clusters seemed to be fine, and the new ones were the only ones where we're seeing impact. We looked at the impacted application and the node they were running on. And after some time, we saw this weird behavior here, right? So ENS6 is the physical device used to egress the VM, and it provides 8 transmit queues to provide better throughput. And as you can see here, we're only using the first one when we should be using the 8 queues. That's weird. And as we dived deeper, by looking at the queuing discipline correlation, we use the default Ubuntu setup, which means we use fq-codel as the main queuing discipline. And because we have 8 physical queues, we also use the virtual multi-queue queuing discipline, which is going to send traffic to the different fq-codel queue. And we're going to have one fq-codel queue per physical device. As expected, because we're only using a single device, we also use a single fq-codel queue, as you can see with the numbers here. And what's interesting is the number of dropped, right? We're dropping about 2% of the packet. And the reason for this is the codel queuing discipline is going to drop packets almost as soon as we start buffering to avoid buffer bloat and additional latency due to buffers. When we saw this, we tested a mitigation, which was replacing fq-codel with fq, and that worked, right? Of course, it's not a real fix because we still can get to the maximum throughput of an instance, but at least we avoided the drop, which impacted throughput of TCP traffic. When we looked at the receive queues, everything seemed to be working fine. So it was only the transmit side that was impacted. So let's discuss our networking setup. We use Cilium in IPAM ENI mode, which means every pod is allocated an IP from the VPC. And then routing is performed on the host so that host traffic is using the primary instance interface and pod traffic is using additional interfaces. So our issue was definitely impacting pod egress traffic, right? This was what we were discussing before. So we wanted to know if other types of traffic were impacted. So we first looked at host traffic, and it turns out host traffic was completely fine and we were using all the queues. We also wanted to know if it was related to the ENS6 interface configuration. So we forced some host traffic to use the additional interface, and this was also completely fine. At that point, we were starting to think that maybe it was related to our CNI setup. And so what we did is we created a network namespace manually, and we configured it and sent traffic through it. And well, this traffic was also impacted, and we're using a single queue, so it was the same issue. We're starting to wonder, well, a VF device only have a single transmit queue by default. By our ENS6 device has 8 queues. What happens if we change the number of queues in the virtual SNA device, which we can configure? And so what we did is we created a network namespace and we're using a virtual SNA device with the same number of queues as the ENS6 interface. And when we did that, it actually fixed the problem. So let's summarize. On recent clusters, we have network issue. Traffic is using a single transmit queue for egress. Because we use FQ Codel, this impacts maximum throughput as soon as we have high throughput because we drop packets. And it only impacts traffic coming through a VF device and routed on the host. As a mitigation, we have 2 options. We can either change FQ Codel and use FQ, which is better but far from perfect, or we can use multiple TX queues on virtual SNA device, but that would mean modifying the CNI code we're running. It's a bit complex, and it's kind of weird also because it used to work completely fine. So how do we debug this? The first thing we wonder is, where should we look? So we looked at the network call stack to send packet to see where the queue selection was happening. And it's happening in the net device subsystem. Here is a very simplified transmit sequence. What matters is we have 2 steps. First step is the queue selection and then transmission. What's interesting here for our case is queue selection is using the select queue function provided by the ENA driver, which we use on AWS. And after that, once the queue has been selected, we're going to go through all this transmit code, including queue discipline management and actual physical plan. But at that time, we're not going to change the queue. So let's focus on this select queue function. So this function is pretty simple. It's only a few lines. And actually, the thing that matters most is the netdef pick takes function, which is the function that is used to compute a flow hash and pick a queue. And it looks like we're not getting there, right? Because this is definitely not happening. We're only using the first transmit queue. So let's look at the test there. So this test is checking if a field of the escape of called queue mapping is different from 0. So for those of you who are not familiar with the kernel networking stack, an escape buff is a kernel structure where a packet is stored with additional metadata, and queue mapping is one of these metadata. So what this code is checking is whether the queue mapping is different from 0, and if it's not 0, it considers that the queue has been recorded. If the queue has been recorded, it's restored by subtracting 1. So now we need to know how these fields evolves as the packet goes through the kernel stack. To do this, we use BPF trace to look at the content of queue mapping as the packet was going through multiple functions. Here we have a simple example for the devQXmit function where we're looking at the SKB and getting the queue mapping fields. And for packets matching a given destination IP, because we can print it for every single IP, we're putting some information, and in particular, the content of the queue mapping fields. Let's do a very simple example. Connect to the network namespace of a pod, to a ping, and here's what we see, right? We go through the probe twice, one in the pod network namespace and one in the host network namespace, which makes total sense, right? But there's only something interesting there, which is the queue mapping field is different in both cases. So let's take a more global look and add probes to more functions. So we went through the call stack of packet egress in the kernel, and there are three groups of functions. The first ones are the ones called inside the pod network namespace as we send traffic from the pod. Then we have the functions called inside the host network namespace as we receive traffic and route it. And finally, once the routing decision has been made, sending traffic through the physical interface. Let's focus on the queue mapping field now. So while we're in the pod, it's always 0, which makes sense because we have a single transmit queue. At the very end here, in the NA select queue function, when we start the function, the queue mapping field is set to 1, which means the queue is considered recorded and restored to 0 and never modified afterwards. And that's why we use only the first queue, which is exactly what we see, right? What really matters now is why do we transition from 0 to 1 here? Because there's no reason as far as I know. What we did is we actually went and looked at the code. And by looking at the BTFGen code here, you can see that we're always recording the queue, which means we should always be impacted. However, we only think this issue on newer clusters. So we wondered, was this always the case? And by looking at the history of the code, we've actually found this commit, which was introduced in kernel 5.11.11. And as you can see here, before, recording the queue was gated by a test, and now it's always happening. And this patch has made it to multiple kernels, and in particular, the Ubuntu LTS kernels. And that's why only the most recent clusters using the most recent Ubuntus were impacted in our case. So how do we fix this, right? First is, well, we chatted with the Cilium team, and in particular with Daniel Borkman, who almost immediately told us, well, this is a bug and we can patch it. And here is the patch that's pretty simple, right? We're just not recording the queue anymore. And we tested the patch and things are now happening exactly as we expect. BTFGen is now not recording the queue. Because the queue is not recorded, in a select queue, we'll call netdev pictx, which will use a lash function to compute the queue. So we're good. What about existing nodes? So the problem with the kernel patch is you need for the code to make it to the kernels we use, which can take time. And there again, Daniel, who had worked on the kernel patch, told us, well, the Cilium agent is already loading EBPF code on the VS devices to perform load balancing, apply network policies. And so maybe we can leverage this program to reset queue mapping and address the bug. And this is the mitigation here. Many thanks to Daniel for implementing it. As soon as we have this mitigation, we're able to build a new version of the agents and deploy it on clusters. And here is what you get. Because these nodes have old kernels which are not patched, VTFGen will record the queue, so set it to 1, which we don't want. However, the new EBPF code loaded by Cilium on the virtual assembly device will reset it to 0 as we receive the packet on the host side. And because it's 0, when it gets to a select queue, it means we'll go through the hash code, which will pick the queue, and we're good. So what about our applications? And as soon as we deployed it, we did tests. And as you can see here, it was immediately fixed, right? We're now using all the queues. Using all the queue was nice, but does it impact our applications? Well, it turns out TCP retransmit, which were high, were now much lower, which was good. TCP retransmit are still a high-level indication of issues. What about the application itself? And as you can see here, the graph is even more compelling. the P95 latency of our application went from 7 seconds to a few hundreds of milliseconds, which of course was extremely good news for us. In conclusion, I mean, eBPF is very powerful, right? I mean, it makes it possible to debug very complex kernel behaviors. I mean, I'm in no way an expert in the network stack of the kernel, but using BPF trace and very simple code, we're able to see the content of the escape buff as it moves through the kernel stack. There are many other eBPF tools, some of them focused on networking, such as Packet, Where Are You from Cilium, but many other. And in addition to being extremely powerful, it's also a very good way to learn about the kernel and its behavior and how it works. In addition, eBPF also makes it possible to patch older kernels without waiting for an upgrades, and that's amazing because waiting for upgrades can take a long time. And even when the upgrade is available, you then need to deploy it everywhere, which is time-consuming and sometimes difficult. So eBPF makes this much simpler. And sometimes, well, it is a kernel bug. I mean, when we started, it was obvious to us it was an issue with our configuration, but it turned out it was a kernel bug. If you're curious, many more details in the Cilium issue linked here. Thank you very much. And if you have questions, I'd be more than happy to take a few. Thank you.
Awesome. I loved how it was presented and the work that you did to actually solve that problem. That was a great investigation. I'm sure it was a little daunting at times though, like looking through like.
It was. I mean, we had no idea where to look, and from what applications we're seeing to the actual issue at the low level kernel, it took us quite some time to get there. But it was also very interesting, and we learned a lot along the way.
Yeah. Well, thank you for that talk. We have a couple of questions. Let's see the first one here. So the first one here is Daniel. Replacing the, I think I'm still seeing preview. I hope we're not casting preview, but it says replacing the FN codal with, actually, let me just see if I can just read this from Slack. One moment. Replacing FQ code with FQ for temp mitigation is interesting. Timestamps on older kernels should be cleared with regard to NS switch. So pacing might not have been effective, I'd presume. Did you look deeper into why that helped a bit, given it separates traffic per flow differently?
So I'm really not a Q-discipline expert. So our hypothesis at the time, backed by the numbers we're seeing on the queues, is that because FQ kernels tries to actively avoid buffer bloat by dropping packet early as soon as the queue is starting to fill. We believe that this was impacting TCP flows, as because packets were dropped, where the window was resized, and we never reached maximum throughput just because the buffer was filling. And when we switched to FQ, the allocation was the same, but we were not actively dropping because FQ doesn't do active drops to avoid buffer bloat. So we believe that this was related to this, but I'm not 100% sure, and I would be very interested in knowing what Daniel thinks about it, because he knows a lot more than I do.
Yeah, that would be a good one. Maybe we could do that on an Echo office hours at some point. It would be great to to do something like that. That would be fun. Well, and our next question. Oh yeah, this was me. So in this investigation, I was noticing, and you did give it a shout out at the end of your slides, but as you were describing the use case and stuff, I know that we have developed an open source tool called Packet. What Are You? And it's a great tool. And I was wondering were you aware of that at the time?
So when we started the investigation, I didn't know the tool existed. So I went to BPF trace because it felt natural and easy, even if at the time I hadn't used it extensively. And then Martin has told me, well, why haven't you used Packet Where Are You? And it seems exactly what we needed at the time. After recording the talk, I actually gave a shot at it, and it's actually very interesting and very amazing what you learn from it, because it instruments every single function we're processing an SKB. Somehow, in my example, I wasn't getting some of the key functions for this bug. So VS xmit, for instance, or ENS select queue. So I don't know exactly why, and I didn't have the time to look deeply into it. But I'm sure we can make sure that packetware you also supports this function, and it's definitely an amazing tool for this kind of use case.
Yeah, and then last thing is in the thread, somebody pointed out, like, it's amazing to me that this bug went unnoticed for so long, and I was like, like, that seems like every Linux kernel bug ever, though. Like, it seems like every so often we come across some bug that's just been there for 20 years, and we're like, oh, you know.
I think this one was only there for a few months, and I think one of the reasons it took some time to notice is before, it's always the same, right? Like it goes into the master in the kernel, and then it takes some time to get into distributions, and so I think that's why it took us a few months to notice. And also you need to notice because you need very high throughput to notice it. And so only a few applications reported the problem, and we run hundreds of them, right?
Yeah,
so I think
that's a great point.
It's subtle and only for some use cases, and you need a very recent kernel to be impacted. And I think that's why it took maybe a few months to notice it.
That's a good point. Well, thank you very much for joining us. And there may be more comments and questions inside of the Slack thread, so jump in if you see them. And I hope you have a great weekend. Thank you very much.
Thank you. Thank you for having me.
Now we are going to go to our first break, and we are going to come back to Tracy and our next section.
welcome back from the break. I hope you use the potty if you need to, grab something to drink if you needed to. We are about to start the eBPF for security portion, but before we do that, we were able to grab a video of the Tel Aviv watch party. So if we could play that really quick, I want you all to see how much fun they've been having. Look at this. I don't even get any of these stickers or t-shirts. Do you hear me? But they look like they're just having a very amazing time. Look how many people are there. That is great. So Tel Aviv watch party, again, thank you for sharing. I really do want one of those t-shirts. And Aisha, you're getting a shout out because if you get one, send me one. Anyway, thank you so much for, again, all of our watch parties. And again, for the people that are in Slack or the viewers, grab that Zoom background. Don't grab the Zoom background. But if you want to share what's going on in your setup, send it to us and we will add it in. All right, so now that we're back from the break, we're going to start our first lightning talk, and it will be, what is it? Oh, here we go. Securing systems with EBPF Linux security module, and that is from Frederick.
Hi, I'm Fred Lawler. I'm a Linux engineer at Cloudflare. Today I'll be presenting on securing systems with eBPF Linux security module. I'm working under the assumption that those attending this conference are familiar with eBPF, so this presentation is more focused on LSM aspects since we may not be as familiar with that. So Linux security modules is a hook-based framework for implementing security policies and mandatory access control in the Linux kernel. Traditionally, LSMs are written as kernel modules, but now we can write them as eBPF without the need to compile a module. So first we'll look into some available options for observability and security detection. Where to find and read LSM documentation, since that can be a bit confusing to locate these. Then we'll look into a use case where we deny unprivileged user namespace creation with the flexible LSM. And finally, we'll look at the performance of this LSM. So let's briefly cover our options. So when working with security, we want to disrupt control flow. Probes and trace points are fine for debugging or alerting on suspicious activity, but can be susceptible to time of check, time of use attacks. In other words, attackers can trick reporting. LSMs can still be vulnerable to these, but not as vulnerable. At that point, an attacker is just trying to bypass control flow. Now, with trace points, you can alter control flow. Not trace points. With probes, you can alter control flow a little bit, but you need a specific option enabled to mutate the return value of these. However, it's not as effective as an LSM because LSMs are actually baked into call paths, whereas probes, you're just working with the actual returns instead. So let's talk a little bit about the documentation. It's kind of spread all over the place. There's not much in the actual kernel documents for LSMs, so really you kind of have to read the source code to be able to work with these. So let's start with lsmhooks.h. This file contains all documentation and description of available hooks. They're essentially organized by categories, binary execution, tasks, sockets, etc. And it's not always up to date because sometimes documentation is overlooked when people contribute to the kernel and update the source. Next one, lsmhook-h, contains the full parameters to the hooks and their order, as well as the full list of registered hooks within the LSM system. So it's always a good idea to look at this file after identifying a possible hook, just to verify that your parameters of what you expect and what you're passing in are entirely correct. Then we have security.h. Security functions often call LSM hooks. So this is one of the confusing things about LSMs, is that the hook names don't necessarily match the caller's name. Definitions of these can be found in security/security.c, and that's a good file to cross-reference hooks against. When looking for LSM call paths, it's also a good idea to kind of search for security underscore whatever name, or just arbitrarily look for some wildcard. So that way you can actually identify all the places where these security hooks are called. So now we're a little bit familiar with LSMs, let's talk about a real-world application of these. So a problem that Cloudflare has, and a lot of other people have, is user namespace creation in an unprivileged environment. This is often used as a first step in an attack against systems, because the Linux kernel is not inherently secure, and there is bugs. And often is the case when exploits are performed, the first thing the exploiters will do is they'll try to create a new user namespace. And the problem is, in between patching the actual problems with the kernel and these attacks, there's a gap. So having the ability to mitigate this, it might be very pertinent to your systems. So let's have a look at how that might look. So when we perform a clone new user, we can use the unshare-ru command to do so. But first, let's look at our actual control flow here. We have ID, which, as you'd expect, returns my current user, group, etc. And if we perform the actual unshare-ru and we perform ID again, we can see that we're now root. This is not entirely true. If we look at the proc self UID map, what we're actually seeing here is we're mapping root permissions to my user. So this essentially allows us to work with kernel functionality that's backed behind capsysadmin. Now, in most circumstances, this is perfectly fine. This is perfectly intended. We don't actually have full root permissions such that we can't mutate files that are owned by root in the root file system. But we do have this shell now has access to kernel features that we otherwise wouldn't have with our own user. So let's track down the hook candidate. So for the sake of this presentation, I already know that create user ns is the function that we're trying to target. For your use cases, you're going to have to probably dig through the kernel code because you have to really identify what you want to protect against and then know where to find that so you can protect against that. And when you do have that function that you're looking for, you can easily open up GDB, perform a backtrace on the function that you're looking for, and you can kind of get a feel for the call path of where you might be able to find security functions. In our case, if we look at the number 2 spot in let's see where we have a call from ksys unshare, we can see that function is located in kernel fork.c. Now we know that because this is located in that file, we can kind of infer that what we might be looking for is a task-based security hook, and we can kind of cross-reference that with our hook documentation based off those categories, and we can kind of find find hooks that we're looking for within there. So let's actually take a look at the kernel/user_namespace.c file. We can see that we have a call to cred equal prepare creds, and then after that, then we make our call to create user ns. Now, since we're kind of looking for a guard, we can kind of look at functions surrounding our actual creation here and kind of see if those actually have a security call within them. Now, I know that prepare creds does. So when we take a look at that, we can cross-reference that with our actual security hook, or not security hook, our LSM hook, and we can kind of see that we do have a case where we have cred prepare here that we can hook into and block our actual call to create a user namespace. This actually exists in the security hooks for task operations section of that file. So let's look at a BPF program. Now that we actually have the hook, we can actually create our BPF program to stop this call path. So BPF programs, at least in the LSM case, they're executed sequentially. So we start off with the ret return ret, if ret return ret, because it's basically an all or nothing situation for whether or not this is going to pass the security or not. But Cgroups is going to change that in the future. There's more to come for that. But for right now, we're sticking with a basic implementation here. And you'll see that we first grab the task. then we grab the syscall that we're trying to target. Now, prepare is called in many places, so we really need to pin down the exact location that we want to prevent. And in this case, it's the unshare syscall. But clone and clone 3 are also can also create new user namespaces with the clone new user flag. And once we have the syscall, then we can check for the actual flags for the syscall. In this case, clone new user. And if we don't have that, then go ahead and pass through, because we don't care for the other cases with this security hook. But if we do have it, then we want to check to make sure, like, hey, look, this user is admin, so they should already be allowed to perform this functionality. Whereas if you're not, then go ahead and disable this. And we do that with the negative EPERM at the end. Now, when we actually run this program and call unshare-ru, we get our error code now, because we are now effectively blocked from being allowed to make this call. One thing to note, the cannot allocate memory error message is does not match with what we're returning. Now, we can look through the source code and easily see that whenever we block this particular security prepare creds call, that it always assumes that no memory was allocated. So we always get this error back. So we'll talk a little bit more about that in a little bit. Otherwise, if we go ahead and run this as root, then as you expect, our namespace is created, and we are now mapped to root in this case. So let's talk about some of the problems with prepare for this LSM. It's called in too many places. All the syscalls, clone, clone 3, and unshare need to be matched against registers. Clone flags also have to be pulled from the registers, and it complicates portability. So in our cases, we're working with x86-64, but if we were to port this over to ARM, we would need ARM-specific magic numbers, etc., to check against. So to overcome these problems, we introduced a new hook called user_ns_create hook, and with a corresponding security create user_ns function. So it really overcomes a lot of these problems, really trivializes our application for this case, because we don't need to perform those extra checks. And we already know that once we're in the create user_ns function, that the proper clone flags and creds and everything else have already been appropriately taken care of for us. So we can check to make sure that we are... So all we need to do is just check to see if we have capsysadmin at this point. One thing to note, that when submitting upstream, make sure to really define your case and how your new hook solves this problem. So that way you can really minimize your pushback from maintainers. And for those who have been following recent news regarding hooks, especially with IO Uring, it's always appropriate to really think about when implementing new features to include LSMs with those new features right out from the get-go. So that way it's always easier to make sure that these get in there before the feature is actually released, as opposed to after the fact. But let's look at performance. So we'll use ftrace for this. Since we're working with the syscall, ftrace is a good tool to leverage. We'll measure with cycles because seconds don't provide a high enough resolution for this small syscall. So we're really going to perform two cases. A control case where we just perform the unshare without the LSM running, and then the second one with the LSM running. Now we only want to measure this as root because we already know that if we're not root, we're already going to get a really reduced it's already going to be really reduced in terms of cycles used because we're blocking the whole context of fork at that point, or clone, or unshare, etc. So we really only care about the performance in the root case. So if you have a lot of programs as root who are creating new user namespaces, this is what we're looking at. So here are the results. Pretty, not really all that self-explanatory, but we're looking at the cycle counts here. So when we look at the actual cycles with the policy applied, we have 70,138. With our control, this is without the LSM enabled, we have 63,294 cycles, and then we have a 6,844 cycle difference. So our hook in the case of root user has roughly a 10% performance impact, which is actually not entirely too bad, to be quite honest. You have to think that when we're creating user namespaces, that's usually once per application, if that. Now, in our case of prepare cred, the problem is that's called in multiple places. So anytime that's actually called, we get this 10% performance impact, especially if callers are root. But with the new user hook, this won't be as prevalent in your actual call path. So, thank you for attending. Happy security.
Thank you so much for that great talk on Linux security modules. Next up, we're going to have Securing the IoT with eBPF and Rust from Giovanni.
Hello, everyone. I'm Giovanni, and I'm the Chief Product Officer at a company called Xane. Today, I'm going to be talking about the current challenges in embedded security and how we leverage eBPF and Rust inside our open source project Pulsar to make the IoT a more secure place. So, what is going on with IoT security and why is it important? The number of connected devices has been growing fast during the last few years. This opens up a very large attack surface on our daily lives, with embedded devices being deployed anywhere from critical infrastructure to automotive systems and industrial plants. The widespread of billions of affordable connected devices also comes with a big problem. When a new vulnerability is exploited on a single device, it takes very little effort to own the millions of copies of that same device that are deployed on the field. We have seen this time and time again over the last few years with the increasing incidence of IoT botnets such as Mirai. Adding to this, manufacturers have also tried to bring devices costs as low as possible, often at the expense of overall firmware quality and security. Traditional tools based on LSMs like Linux and AppArmor have not helped a lot either. They are rather complicated, not very flexible in what they can provide, and even worse, they're hard to deploy, requiring that you recompile the whole kernel every time you need to update them. For these reasons, it's not really a surprise that they are among the most disabled features by sysadmins. So what can we do to create a safer IoT landscape? eBPF is the perfect tool to obtain deep visibility inside Linux devices thanks to its near-native performance and increased safety over kernel modules. The increased portability of BPF programs across different kernel versions is a deal-breaker feature to develop solutions that can scale to the plethora of IoT distributions out there. With granular access to each individual running process, eBPF helps us understand exactly what a device is doing at any time, and allows us to build effective security logic on top of the rich data sets that we can collect in real time. In order to make the power of a BPF as accessible as possible, we at Xane are developing Pulsar. Xane Pulsar is an event-based security observability framework designed for embedded Linux devices and built in Rust. At its core, Pulsar is made up of modules that make use of eBPF to collect information about application behavior from the kernel and transform this information into events. Every event is then validated by the built-in rules engine that lets you define the behavior you want to identify as a threat. With Pulsar, you can easily monitor in real time the activity related to processes lifecycle, networking, and file system operations. And its modular architecture makes it very easy to extend, customize, and maintain the separate Pulsar modules. This separation of concerns also ensures that the whole application is resilient in the event of failure of a single module, and that you can decide the amount of information you want to keep track of without causing excessive overhead to the host machine. Pulsar supports the most common architectures found in modern IoT devices, including x86, ARM64, and RISC-V. One of the advantages of Pulsar is that it is written in Rust. Rust is a modern programming language, particularly suitable for low-level applications. With Rust, you can combine all the new features of modern languages without having to give up on low-level access to the host resources and excellent performance. Memory-related bugs in C and C++ systems often result in CVEs and emergency patches. Rust was designed to remove most of these software development security concerns at their root, especially the ones related to memory and concurrency. The Rust eBPF ecosystem is also growing a lot with exciting projects such as Aya and BPF Linker. This makes Rust the perfect programming language for developing eBPF-powered security-critical applications running inside constrained embedded systems. Thank you, and if you like the project, check out Pulsar on GitHub.
All right. Thank you so much for that talk on securing the IoT with eBPF and Rust. And you said Rust, so I know you should have no problem with questions in Slack. So everyone keep those questions coming. We're going to have our next talk, and it's container security and runtime enforcement with my favorite little shield dude, Tetragon. And that's going to be given by Jalal.
So thank you very much for joining me in this EBPF Summit 2022. I'm Jalal Harouni. I work at Isovalent. And in this talk, we are going to see container security and runtime enforcement with Tetragon. So Tetragon is an eBPF-based security observability and runtime enforcement. It can achieve deep visibility and runtime enforcement at different layers. So not only on the system calls layer, but at many different layers and subsystems of the operating system, as shown in this picture. Tetragon uses BPF and BTF. So BTF is the metadata format that encodes debug information that is needed by Tetragon BPF program. Tetragon can use the default BTF file of the operating system and also ship some BTF files that can be used by its BPF programs. In Kubernetes and containers context, Tetragon, when it collects its events at the kernel space, it will associate all these events with processes and eventually with containers and pods. That allows users to better understand what the Kubernetes cluster is doing, what are the security events, etc. Tetragon uses kprobs to dynamically break into any kernel routine, so we can insert capabilities checks without changing kernel code. We can harden the kernel code, detect exploits or bugs. This also allows to trust process execution, trust system calls, and trust capability checks performed by the kernel on processes. So if you want to know what capabilities your container or your application may require when they are running, Tetragon is a good choice as shown in this demo. So we have the sucomod inside the container that triggered the capability check done by the kernel, what was the capdac read search inside the user namespace level 1, meaning it's a nested one owned by user ID 1000. That is an unprivileged user namespace, and the result is 0, concluding that the capability check succeeded. This allows in the future to build better security profiles with the capabilities that your containers may require. Tetragon can also filter system calls and block dangerous system calls, support the default Docker seccomp profile as no allow or deny list. All this can happen on the fly without the downtime or requiring container restart. Tetragon can also stick access to Linux namespace. So we have the user namespace that allows users to create their own namespace and gain capabilities in order to access some kernel features. And often attackers take advantage or abuse this in order to perform kernel exploit privilege escalation or container escapes as shown into this list of CVEs and exploits. Tetragon is able to restrict creation of unprivileged user namespace, and it will kill the offending process as shown into this demo. So Tetragon can also restrict capabilities inside namespace. So this demo shows how PS inside a user namespace, when it tries to access information about other processes, capsys petras, it can be killed. Beside the tracing capabilities, detecting new capabilities or racing capabilities, Tetragon can also block loading kernel modules as an example, or auto-loading vulnerable or old unpatched kernel modules. Tetragon can also attach to Linux security modules hooks on the fly. One of the nice features is it can update the security policies of your Kubernetes cluster on the fly without downtime, meaning it doesn't require container or an operating system restart. Besides attaching to the capabilities LSM, it can also take advantage of the kernel lockdown LSM, which is an LSM that blocks or gates access to a running kernel image. Tetragon can take advantage of its hooks by restricting loading inside kernel modules, restricting kernel execution of inside images, etc. It can also gate access to the set user ID system call group in order to allow only some user IDs. So Tetragon sandbox allows to enforce runtime restriction in order to prevent container escapes, prevent the kernel exploits, and it is easy to adapt to new techniques or exploits. From our summary, we can say that Tetragon can restrict system calls, can trace or restrict capabilities and namespace as usual. It's easy to attach to Linux security modules and perform security checks. And we can be easily used to harden the Linux kernel and insert capability checks at random place without changing kernel code. Our conclusion is EBPF-based security and observability solutions are flexible, and they allow us to adapt the policies and behavior on the fly without service downtime. Thank you very much.
I'm going to go back and watch that talk because I'm still learning about Tetragon. So thank you for that. Our next talk is going to be using eBPF in system security, and we're going to get that from Lee and Zufeng.
Hello everyone, my name is Licha, and in this topic I will talk about the EBPF usage experience in system security with my colleague Xufeng Zhang. We are both from Ant Group. We will talk about the security issues we want to resolve and why we choose this EBPF. Finally, we will introduce our EBPF-based security platform. These are the four major kinds of security issues we want to resolve. We want to decide the default hardened options of Linux kernel and mitigate Linux kernel vulnerabilities. We also want to detect and prevent container escape and Linux malware. All of this need kernel detection and prevention. A kernel hardened decision, as we know, it's difficult to decide which hardened options should be set, as there are a lot of applications running cluster. Every small change in kernel may cause unexpected consequences. So should we disable user namespace creation? The EBPF can tell the answer. We can attach EBPF to system and collect the access log. After analysis the access log, we can make the decision to disable user namespace or unprivileged user for the FD. As we also know, it's not easy to patch Linux kernel vulnerabilities in production environments. However, we need to process these vulnerabilities, as it's easy to do container escape in container leveraging these vulnerabilities. We can use BPF to leave patch the kernel. Of course, this needs BPF LSM. We can first analyze the exploit and then generate a BPF program, then attach to system. So after that, our system can stop this attack. Container is popular these days. Container escape is not uncommon. There are also misconfiguration can lead to container escape. For example, the user mode help. We can detect and prevention container escape as following. For example, for the user mode help escalation, we can attach a cable of EBPF to the kernel function called user mode help setup, and inspect the access log to find the suspicion call of it. Nowadays, Linux malware use a lot of advanced technologies such as fileless, BPF, and rootkit. We can use BPF to detect this malware quickly and easily. For example, for the fileless attack, we can attach a source called EBPF to memfd create. Okay, so let my colleague Xufeng Zhang to talk about our EBPF-based security platform.
Okay, after Li Qiang discussing about the 4 major threats, now let me introduce our BPF uniform platform. I'm Xufeng Zhang from Group. So, to resolve all the above security issues, we need to install different kinds of BPF program for the whole cluster node. And for the sake of minimize performance impact, BPF programs should be made fine-grained and loaded on demand. Moreover, BPF must be flexible to schedule and easy to use for end users. Thus, a policy language is also needed. So, in order to meet all the requirements, we developed a cloud-native BPF orchestration platform named BPF Shared, including a Kubernetes operator and a BPF manager daemon set. The workflow begins with a user-provided policy YAML. The policy is a Kubernetes custom resource definition. After the policy is created, the operator is triggered and it passes a rule in the policy, converting them into BPF artifact. The BPF artifact is another Kubernetes CRD. It consists of BPF program and mapped data. In the daemon set side, there is also a Kubernetes controller, which watches the activities of BPF artifact. When the BPF artifact is ready, it fetches the content of BPF artifact and calls the loader to load the BPF program and map data into kernel. All the BPF programs shares an identity-based rule engine to do filtering and output audit events. Let me make a summary for this talk. As we can see, BPF is powerful and useful in system security, and we have implemented a uniform platform to make BPF used in system hardening, system log patching, container execute monitoring, and Linux malware detection. Thanks for your time.
All right, thank you for that wonderful talk. Our next lightning talk will be Applied eBPF for Cross-Platform Security Research, and we're going to hear from Dinesh for that one.
My name is Dinesh, and I work at Microsoft. So the opinions expressed here are solely my own, and it does not necessarily belong to my employer. So let's start with a typical use case of applying eBPF. Say I, as a security researcher, want to log all the syscalls invoked after a specific incident. It could be execution of a binary that I want to analyze. It could be a malware, or it could be something that I am trying to do vulnerability research on it. And I want this to happen non-intrusively across the system, so that I should be able to record the raw data points, which can later be used to create insights or to act as a base data for creating deep learning tools or any other research frameworks. If you see, it would be something similar to Regshot for Windows. Regshot is a very popular tool, as many of us would know. In Windows world, where before running a malware, we would run Regshot to take a pre-snapshot and then run the malware and then take a post-snapshot. It will capture all the file systems, Windows registry before running the malware and after running the malware, and then do a comparative study to get a report of what has actually transpired while running the executable. So at the outset, it might seem very simple, and in fact, it is one of the common use cases. However, let's take a deeper look. So this would be a typical flow where we would take a snapshot, pre-snapshot, capture all the files in the target system, and then kernel data structure and other significant files that corresponds to certain automatic actions that can be done, like scheduler. And then we will run the binary. Then we will again take a snapshot. We will make it pass through an active noise filter that captures, that eliminates all the common events that happen as part of the normal system execution. And in the at the end, we will get a system report. So and this has to happen non-intrusively. If we can quickly take an analogy of Heisenberg's uncertainty principle, right? Like Heisenberg particles. Very famously, we used to hear you can either know where the particle is or how fast it is moving, but you cannot know both. The reason being that the particles are so sensitive. In the process of measuring it, you would be displacing it. You would be emitting light on those particles. Those particles are so tiny, the projection of light on them displaces it. How we calculate the temperature of water, say for example. If we put a thermometer in the water, the thermometer actually draws heat from the water to show the temperature. In this case, it is negligible because the water body is large and the values are larger, and the amount of temperature the thermometer draws is negligible. So similarly, when you want to do some real-time event analysis for security observability problem, you have to take this into consideration, that you are not intruding in the normal flow. And more than that, there are certain limitations with the ptrace and LD preload, which are like typical hooking techniques for process-specific interception. And more importantly, the ability to handle polyglots. We will quickly discuss what is polyglots. So specifically, we will talk about Golang. Golang, as we all know, is a ultra compatible modern language. Just with a single build script, it can generate 40 different executable that can run on 40 different operating system and architecture combo. So it has such a powerful cross-compiler support from the same system. You will be able to generate for many number of flavors and architectures. So naturally, it's a great choice for security researchers, and automatically it makes it as a great choice for malware authors as well. We have been seeing a constant increase in the malware which are generated by Go language. So one of the key challenges that Go language built executables pose to security researcher is that if you try to do typical ptrace on them, you would get this message saying that unable to inject library into the process because it doesn't have libc in it. So for this demo, we have taken some 7 languages and built a hello world program. It simply reads a file, and we want to put a typical hook and then see how do these executables behave. And we will then run the same demo with the EBPF to showcase how seamless it can become to observe something without much effort. So for the benefit of in the benefit of time, because we have only 15 minutes, I have already recorded these demos. Let's quickly skim through these demos. Say, for example, now let's ptrace an executable which is compiled with C language compiler. You run it and you observe it. So you just put a ptrace hook and everything works fine, no problem. But if you want to do the same thing for Go, so now what you do is you try to put the same ptrace attach, and you get the message that it is not able to inject into the library. The same thing would happen if you try to attach a GDB. You can't break on the library call like how you typically would do for other executables. So now let's do the same demo with OpenSnoop, which is one of the eBPF utility. And in this case, you can just start the probe, set up the probe, and then you can start to run all the 7 executables one by one. And you will be able to observe that BPF probes doesn't have any issues with respect to tapping all the syscalls that is executed by these executables. So it is kind of non-intrusive, and it doesn't need to go through a lot of efforts. You just place the probes and then get the results. So now we have established the base. Let's observe a ransomware execution through eBPF probes. So the goal for us in this exercise is to reconstruct the flow of a multi-component file encrypting ransomware. In order to make it more interesting so that we can showcase the power of eBPF and the smoothness with which we can collect various probe information, we have developed each of these components in different language. For example, the file dropper is written in Rust, the downloader which the dropper drops is written in C, and the downloader eventually pulls up a file encrypting ransomware which is written in Golang. So in order to run this demo, we have set up this lab environment where we are running, we are hosting the file encrypting ransomware in one of the made up CNC, and then this is the victim machine, and there are some other machines in the same intranet. So let's quickly see this demo. So as you could see here, we are setting up some of the probes for open syscalls, and then xxsnoop is nothing but it sets up sysclone syscall tabs. And once all these probes are set up, we can run the dropper, which will start a chain reaction of dropping and then downloading and then encrypting the files in the disk. So now let's start the dropper. And as you could see, all the information is captured. And in order to make it more intuitive, let's plug the graph module to the eBPF output. Basically, what we are trying to do is once we have established the probes and the trace points, the output that is streamed by those probes and trace points are plugged into the graph module, where we use a Neo4j as our backend. And the information streamed by these probe BPF trace and OpenSnoop and xxsnoop, we are converting it, we are representing the knowledge as a triplet. A triplet is nothing but we are representing entities, and then the relationship between entities is represented as edges. So this naturally builds a knowledge graph organically, so that for an analyst it will be easier and intuitive to reconstruct the execution flow. Let's quickly see that in action. So in this case, you could see that all the information are actually captured in triplets and then converted into nodes and edges. So during the execution of this ransomware, there are 6 processes. So you see 6 nodes here. You can start from the bash, which started the execution, and it has dropped the dropper. And when you expand the dropper, it has downloaded the payload zzz.bin, and the zzz.bin is again downloads payload.bin, which is the Golang return binary. And if you expand the payload.bin's image path, you get to see that it is actually touching all these files, which are nothing but the GOAT files that get encrypted by this file encrypting ransomware. So now you will be able to intuitively associate the relationship and how this executables accomplished the task of infecting the machine with file encrypting ransomware. So with that, let's quickly move on to the Android part. So eBPF and Android has been talked about a little in the community, but it is a little challenging because the kernel, in order to make Android's kernel to support eBPF, it requires some of these flags to be compiled with while we are building the kernel for our target machine. In this case, we are using Pixel 4a, Pixel 6a, and emulator that runs Android 12. Pixel 4a was running Android 12, and Pixel 6a was running Android 13. So these flag details are provided in the BPF trace repositories page as the check kernel features. So once we build the kernel that supports the eBPF modules, we can really make use of the rich tools and the powerful tools it produces. That is where the analogy that I gave about observing something without disrupting the actual values. Because when it comes to Android, because of the restricted ecosystem, the monitoring and the security observability becomes a little difficult because we often end up slowing down the system. But in this case, the slowdown is not significant. Let's quickly see 2 demos. So once we have established the K-probes, say in this case, we are using BPF trace front end, and we are setting a trace point on syscenter open at syscall. And this is not something that you can limit with one syscall. You can use as many syscalls as possible, and then you run you run an Android APK file which is protected by commercial protector, or you want to do vulnerability research, you want to see what files it uses and how it uses. So you will be able to trace it seamlessly. In this example, as you could see now, we have set the trace point, and then we are starting the SMS application, and we will be able to see it, how all the different syscalls that gets called as part of the execution of the file that we want to analyze. And similarly, we can use a real device and observe the traffic in real time using TCP Connect. So as you could see here, now we are setting up some open syscall tapping using OpenSnoop and exec-snoop for sysclones, and then TCP Connect, which is also a BPF helper utility. Now I run the actual browser in the device. Actual browser in the device, and then we browse to ebpf.io, and we can see the traffic in real time, how it is captured. Yeah. So I hope we have covered quite a bit of ground in the limited time we had. So I'm open to any queries you may have. This is a very interesting framework, and I have been trying to learn it for the past few months. So yeah, I'm looking forward to learn together with the community. Thank you, everyone.
All right. Thank you so much for that talk, Dinesh. And for our last lightning talk of this segment, we've got analysis of offensive capabilities of eBPF and implementation of a rootkit from Marcos and Juan.
Hello everyone, my name is Marcos Bajo. I'm a master student of cybersecurity from University Carlos III Madrid. And well, the presentation today is based on my bachelor thesis that I did some months ago under the supervision and advice of Dr. Juan Tapiador, who is a professor in computer science and also the lead researcher of the computer security lab here at University Carlos III Madrid. By the way, he will be also joining us during this talk. So during our presentation today, we will be discussing how malicious actors can leverage eBPF for offensive purposes, and how we have implemented one of the first ever eBPF rootkits out there, which we call Triple Cross. So here's a quick overview of the topics that we'll be talking about. First, we'll discuss why this talk is relevant for the eBPF community. Afterwards, we'll explain the offensive capabilities of eBPF and how we have created our own rootkit. And finally, we'll give you some tips and discuss some techniques about how you can protect yourself from malicious eBPF programs. So let's start with it. First of all, many of you may know already about Linux kernel modules, LKMs. Essentially, it's the old way of doing what we do with eBPF, when instead of running sandboxed eBPF code, with LKMs code is just run directly into the kernel. Now, of course, this means that because LKMs have full control over the system, they have historically been one of the most popular ways of building rootkits. Now, nowadays you won't find LKMs available by default at any critical system, but you will definitely find systems with eBPF by default. So the obvious question, and the one we are trying to solve here, is, could a malicious eBPF program ever turn into a rootkit? Alright, so we keep mentioning rootkits, but what is a rootkit exactly? Well, it's a special type of malware that specializes in two main capabilities. First, rootkits are known for being stealthy, meaning that they hide their files and activity from the user and any monitoring software so that they remain undetected for the longest period of time. And secondly, they typically include a backdoor and a command and control system, allowing attackers to remotely control the rootkit from their own machine. Now, it's time to answer the question, can eBPF be used for building rootkits? Unfortunately, yes. We found that during 2021 and 2022, there have been a series of reports about rootkit attacks targeting systems worldwide. VVP47, BPF-DOORS, and Biot are all names of rootkits that have already been using classic BPF filters and also modern eBPF programs for their malicious functioning. So our goal in this talk is therefore to uncover how threat actors are leveraging eBPF for malicious purposes so that the community is aware of the risk and security researchers can understand the threat and protect their systems. So let's start now with our analysis of offensive eBPF. We'll assume that you have previous knowledge using eBPF. Also, we have very little time, but we'll answer any questions after this talk. So first of all, what you see here is the memory of a process. Essentially, it contains everything that a process executing a program needs for it to be run. So this is the text section, which contains the instructions of the program that is being executed. And this one here is the stack. So here's where you can find variables and other data that is used during the program execution. So as you will know, if you have been using eBPF for a while, we can create different interesting programs in eBPF, such as kprocs, trace points, that allows us to hook the execution of a function and perform different operations in that context. So here you can see that our process is executing the system called openat, which is in charge of opening a file whose name we have stored in the stack. Then eBPF allows us to hook the execution either at the start of the kernel function or at the end. Now, once we are inside an eBPF program, we can read the arguments of the function. How do we do this? Well, we have the BPF ProRead user helper, which reads memory at the user space, or the BPF ProRead kernel helper, which reads memory at the kernel space. Now, the eBPF verifier, as you know, restricts what and how you can read memory. But in our experience, if an eBPF program wants to misbehave and read out of these bounds, well, it's possible. So the way we do this is by taking the argument of a hook function as a starting point in the virtual memory of a process, and then we can proceed to read memory at different offsets from that starting address stack using BPF ProRead user, as you can see here, performing what in essence is a memory scan. So as you can imagine, using this process, we can find sensitive data such as secret tokens at the process, Moreover, because there are a lot of other data, such as return addresses, the stack, which leads to the text section, this is key for an attacker which seeks to hijack the process execution, as we'll show you. So it's not only that we can read memory from the same program, but also we are able to modify data at the process virtual memory using BTFGen ProWrite user. As you may know, there are 6 restrictions over which memory sections you can write into, essentially only those marked as writable. So for instance, you couldn't modify the instructions, but you could definitely find yourself modifying data at the stack. So there are 2 issues with this helper. The first is that malicious EBPF program can write into the function arguments of the function before the kernel execution. So what happens is that you modify the kernel execution. And the second is that, just as with the reading helper, we are not restricted to write only the function argument, but rather we can specify an offset from that address and write into that. So in practice, a malicious EBPF program is free to modify any writable user memory it will. And the takeaway here is that this is a very powerful primitive, and we'll definitely show you some of its use cases in our rootkit. So let's discuss networking programs. As you know, we can create EBPF programs that receive the incoming traffic, such as XDB programs, and also programs that monitor the outgoing traffic, such as TCA-REST programs. Now, these programs can drop or modify the data at any packet, although in principle, as you know, and this is very relevant, we cannot create new packets. However, the issue is that we found that by taking advantage of the retransmission mechanism of the TCP protocol, we can actually generate arbitrarily new packets by overwriting any packet with malicious data and then waiting for the TCP timer to time out so that the original packet is delivered to. Now, in practice, this means that a malicious EBPF program can potentially control and modify all the traffic on the affected machine, just as we will show you in our rootkit. So let's see now how we can weaponize these capabilities in a real rootkit. We talk about dangers of having the BPF ProWrite user helper written user memory, but okay, many of you may argue that because the text section is not writable, then we cannot modify which instructions are being executed, right? So in principle, it should immediate dangers. Well, the truth is that you can actually modify the instructions being executed with this helper, and we'll do this while implementing the library injection module of the rootkit, whose goal is to execute a malicious library by modifying the memory of a process. So when you want to execute a system call in a process, you don't just get from the text section to the kernel, but rather for calling the system call, you first get to a special section in memory called the PLT, which is some data stored at the GOT section, which is used to find the path that leads to the kernel. Now, what would happen if we overwrite the GOT section? Well, this is exactly what we do in our rootkit. In this technique, we call GOT hijacking. So basically, we overwrite the global object table so that the PLT now points to a malicious library of our own, executes malicious code, and then restores a normal execution. So if you follow the right lines here, we can see that the execution still reaches the kernel, but it goes through our malicious code this time. So the details are highly technical, but just so that you know, we perform 5 different steps during this attack. So first, we scan the stack using the reading helper using offsets. Then we locate key functions at the glibc library. Then we write our shell code into code cave. Afterwards, we overwrite the GOT section. And finally, we execute our shell code, which leads to executing our malicious library. And then we return back the execution to the original process. So now Dr. Topiadoro will be joining us to cover the rest of the rootkit modules.
Hello everyone, let's go on now and describe another of the rootkit modules, the privilege escalation one. Our goal here is to enable the rootkit to execute any arbitrary code with full privilege. Essentially, EBPF doesn't allow us to tamper with the pseudo system as a kernel module can do, but we can instead modify the data that the kernel reads from the pseudoRT file. The idea here is that we inject a malicious tracepoint program that modifies the data read from the pseudoRT file so that those programs the rootkit wants are always able to run as root. Also, we wanted to build a small proof of concept on how EBPF can be used to run malicious programs. I mean, we know that you cannot use EBPF to directly execute a program from the kernel, but what if you could modify existing execution calls so that you control which program gets executed? Well, that is exactly what we are doing here. We modify the exec via system call so that a malicious program is run instead. We do this following a special technique that we describe in the paper this talk is based on, and the injected code can reproduce the original program execution, and therefore this process is stealthy. Okay, let's now talk about the backdoor and command and control system of triple cross. As you can see in the slide, this is also a very complex system, but basically we have designed three components. First, we have one XDP program that hides malicious traffic and is in charge of executing the commands that are received from the network. Then there is a TC egress program that modifies the outgoing traffic. Second, we have a series of what we call backdoor triggers. These are special network packets which are designed to be stealthy and not to be detected by network defenses. We use this to indicate the backdoor which actions and commands to execute. We have also implemented several remote shells that can be executed after receiving a trigger. These shells might be used by the attacker to execute commands on the victim. We have implemented a classic reverse shell, a plain text shell, an encrypted one, and finally something that we call a phantom shell. In this case, instead of generating new packets from user space, what we do here is to make use of the TCP retransmission technique that we described earlier, so that both malicious and legitimate traffic are delivered using only one eBPF program at the kernel. We'll see an example of this during our demo. With respect to the persistent capabilities, we use two well-known techniques. First, we use the cron system to ensure that after our reboot, an automatic process will install the rootkit again. And second, we use the sudo system to ensure that the rootkit is loaded with root privileges. To hide the rootkit files themselves, we included in the stealth module some more tracepoint programs that tamper with system calls and hide the files and directories belonging to the rootkit. The result is that the rootkit is both stealthy and persistent. And now it's time to see our demo.
So we have prepared two virtual machines, one in which we install the EBPF rootkit and another one from which we will attempt to remotely control the rootkit. So what you see on the screen is a simple program that just counts up to 6. The thing is that it makes use of a system call, and we will attempt to hijack its execution via our GUT hijacking technique. So first we start listening from the attacker machine and install our EBPF rootkit, and then run the program again. As you can see, the program runs successfully, but our library gets injected. Our library then spawns a remote shell to the attacker machine from which we can execute commands remotely. Another thing we have implemented is the rootkit client. It's a program you can use to remotely control the backdoor. Here, for instance, we are creating an encrypted shell from which we can also execute commands remotely. And finally, we wanted to show you the phantom shell. If you remember our explanation, basically we don't generate new packets, but rather we overwrite existing traffic and make use of the TCP retransmissions technique. So as you can see, we are not receiving any answer because there is no traffic at the infected machine. So we'll go ahead and generate some packets by visiting the EBPF IO website, and only now we hijack some packets, and as you can see, we receive an answer. And to execute new commands, the only thing we need to do is to generate some new traffic so that it gets redirected to our machine. So here you can see we received result of the command after generating some new traffic.
All right, let's now briefly discuss some tips about how we could protect from the type of malware that we have introduced. First, network monitoring. You could use an intrusion detection system or a firewall in order to detect suspicious communications belonging to the rootkit. But know that if these defenses are located at the endpoints, then the rootkit can hide incoming traffic with an XDP program. Second, we can also monitor the BPF system call in order to detect whether there is a running eBPF program performing some malicious activity. For instance, you could do this using BPF tool or eBPF kit monitor. And finally, please keep in mind the principle of least privilege. You don't always need to give full root privileges to eBPF programs. If a program is only supposed to be working with a network, maybe it shouldn't be able to load keyproof programs and vice versa. We have capabilities exactly for this purpose. There is also another solution, which is something we stumbled upon while doing this research, and it's the possibility of signing eBPF programs. There is an article by Jonathan Corbett, which we are leaving here, and we believe it could be useful in order to ensure that only eBPF programs made and tested by a trusted party can be loaded into the kernel. We want to end this talk by saying that even if we monitor the network and the BPF system call and so on, there is still still exists the possibility of having a rootkit going unnoticed. In theory, because the rootkit is already at the kernel and because eBPF offers virtually the same capabilities as an LKM, then it is possible for it to tamper with any monitoring software installed. And it could definitely tamper with any access to the eBPF system call too. So one takeaway from this talk is that eBPF offers interesting offensive capabilities that we need to better understand and counteract. So we have reached the end of our presentation. This is the link to the Triple Cross project and the thesis paper where you can find all the details and all the sources about what we have been discussing here today. Thanks for having us, and now we'll be happy to take questions.
Things that happen off camera. Anyway, as you heard, don't let your guard down. EBPF malware is a thing. But seriously speaking, well, I mean, I'm being serious, but seriously speaking, also, Duffy was very interested in this talk, so you should have some questions coming from Duffy about that one. That was our last lightning talk of this segment. So we're going to have a break, and you want to make sure that you're back in time at 10:40 PT because Liz and Duffy will be bringing you all Capture the Flag #2. Hope to see you soon.
Hello and welcome to the Capture the Flag segment from the EBPF Summit today. So yesterday, if you were watching, you might have seen us announcing the two challenges, number 2 and 3. You can still find those challenges if you go to isogo.2/CTF2022. And in this segment, we're about to run through the solution for challenge number 2. So if you still want to work on that, you might want to just turn the volume down, maybe close your eyes for 10 minutes, set yourself an alarm so that you don't miss anything else that's happening in EBPF Summit today. Before we go to the solution, let's just congratulate a couple of folks who have already solved challenge 2 and challenge 3. So the first person to post the image saying that they had solved challenge 2 was Andre Letterer. So congratulations to you, Andre. And then later on, in fact, I woke up to check the Slack channel this morning and PJ had solved challenge number 3 at some point overnight. So congratulations and well done to PJ. Brilliant work for both of you. I know there are several other people who've been posting the fact that they've solved those challenges. So hopefully you've enjoyed doing that. And now I would like to bring Duffy in because Duffy's going to help me solve challenge number 2.
Yay. Yeah, earlier today, Liz and I recorded the way that we solved challenge number 3. I haven't done number 2 yet, but I worked through challenge number 3 live with Liz, and it'll be recorded and presented as Echo Office Hours this Friday. And I have to say, I'm impressed, PJ. That was a tough one. I'm probably impressed by the solve of number 2 as well, given the context. But
so I think challenge 2 is a bit easier than challenge number 3. So I'm going to be driving, but Duffy is going to tell me what I should do. So, and I'll try not to give too many hints along the way. But if I've already got the virtual machine installed and ready, so here we are with the instructions that say we're not going to need any Kubernetes knowledge for this challenge. I am already SSH'd into this VM, and our clue here is, like a treasure hunt, in this challenge, a map will show you the way. So, Duffy, what should we do?
Well, my initial impression is definitely BPF maps, which are our way of holding data and making it available to BPF programs, or even to copying data back and forth, output of BPF program and back into user space, that sort of stuff. So I would think that we would want to look at the maps that are on the VM. So if we do BPF tool map list, I think it is.
Map list. We're going to need to sudo that.
Yeah. Sudo make me a sandwich. Oh boy. That's a lot of maps. Oh, hey.
We have.
That is a lot of maps, but number 220, there is a map that is labeled name Summit 2022. There are also some other maps in there like Cilium policy, BPF for read-only data, CTF flag.
CTF flag. That's
surprising.
Kind of interesting.
But let's take a look at Summit 2022. So let's take a look at that map. How do we do that? Let's do BPF tool map help.
Okay.
Okay. So the map object is referred to by name, map name, or ID, map ID. And then some things we can do to it. We can push pop
maybe
peek.
it's further up. Here we go. So we can do show, list, create. We don't want to create one.
Let's do BPF tool map dump. But before we have to do that, can you scroll up again? What was the ID of that map that we saw that had the name? Or do we want to do it by name? So yeah, let's just do by name.
Yeah.
So
we're
BPF tool map name, the word name, and then the Summit 2022, I think it was.
Okay. All right. Interesting.
Right. So we have a key value in here, and this looks like hex. So what I would do, because I'm lazy, is I would actually copy the hex and go to a website that would convert this to text. But I'm sure there are more handy ways to do it.
I've got a little trick up my sleeve to do it in the terminal. So we're going to take those characters and
this one I don't have committed to memory. Yes.
So if I just copy, oops, those. There's probably a better way of doing this as well, but
because word wrap or whatever.
Yeah. Oops. Oh, I hope the. Okay, there we go. It did work. So it says run chmod on a file. So what could that be talking about?
Well, so this is still a deployment, right? So like it says you don't need a Kubernetes knowledge for this challenge, but let's.
And you don't. You shouldn't need any Kubernetes knowledge for this one. I'm going to keep us away from Kubernetes.
All right. Can we look at the? Can we look at the log of the container that's running and just see what it has to say for itself? Or is that too much?
I think that might be taking us down the wrong direction. Yeah.
Okay.
So one thing we could do is we could have a look at the
which file?
The hints.
Yeah, let's try that.
Okay. Actually, I should have shown this earlier because one of the things that we've got here in these capture the flag hints, we've also got the background story. And I just want to give a shout out to Quentin Monet, who wrote the background story last year and then continued the story for us this year. So, and I
also he's just a generally awesome human. Yeah.
Yeah, and he maintains BPF tool as well. So shout out to Quentin. I particularly like this bit about that, you know, we despise fighting off glimworms that came to eat our giant bees. Anyway, this text is great and fun, but doesn't actually contribute clues. So I'm going to skip over it. We're already running. We said a map will show you the way. We haven't solved it yet. This hint is a hint about BPF tool. Let's see what other hints we get. Okay, so I think what we did here was we found a map. We took a step. We've already decoded those ASCII characters. So I'm going to click this clue. Okay, so maybe there are other useful maps.
That's an interesting hint. Can you go back a second? I want to see what the second hint would have been.
This one?
Yeah.
This one would have been a hint that maybe there were some characters.
Oh, because it's hex. Got it. Okay.
Yeah. Yeah.
Other maps might help. You know what? Maybe I'm thinking about this the wrong way. Maybe. So in BPF, we're looking at like event data, right? So like when we are using BPF, like when you hook into a thing in the Linux kernel, you're basically just watching an event stream for things that are happening. And then in some cases, you're able to make modifications to the thing that is passing by. And in other cases, you're really just kind of announcing that this thing has happened or making some change like that. So because it's event driven, the hint I think might make a little bit more sense because it says run chmod on a file. It doesn't say which file.
So what if we were to assume that since we're at the EBPF summit, maybe there is some BPF programs involved?
Yeah. So let's just pick any old file and chmod it. Like let's make a new file and try this and chmod it and see what we see.
Okay. So if I do something like I could just do touch.
Like make temp or something. Yeah.
Text. And okay, so if actually before we do this, I want to just explore a little bit about the BPF programs that are there. So let's have a look and see what programs there are.
That's a good point.
Yeah. Okay. So there's a whole bunch of things.
Bunch of Cgroup attachments, which is expected in a Cilium-based cluster.
Yeah.
There is a trace point. What is that?
Yeah. Yeah. So I think this one is kind of interesting. Now, also what's interesting here is it refers to a couple of maps. And I think if we looked at the maps again,
220 and 230, yeah. Like if you do BPF lists, ID 220 and BPF list or BPF show, I guess map show.
let's have a look. If I just list them, we'll find 228 is this one.
Oh yeah, there's the CTF one. So there are two
Okay.
that are made by the same trace point. And a trace point is exactly that thing we were talking about. Like if it would basically hook into a particular function and then make something happen when that thing comes by.
And one thing you can do with trace points, which is pretty neat, is we can also list them with a thing called perf list. So this shows programs that are attached, or trace point type programs and kprobe type programs.
Haha.
And I think that's giving us a pretty big clue.
Yes, it is.
So we don't know what this program does, but we know that it's attached to chmod, and maybe that's related to that clue that we had about running chmod on a file. So should we go back to your previous idea of running chmod on that?
Let's give it a try.
Yeah. So, all right. So now what?
So now I think I would look at the log for the pod to see if anything has changed, or maybe if, but we did see two maps there, right? And we did see the reference of both maps. So what is the content of the map, for the second map, the CTF flag map? Is there anything in it?
Should we do map dump again?
Yeah.
And it was called CTF flag. And there it is.
Hey.
The flag is RTD2. And we can just confirm that we got that right by putting it into the type form.
It was interesting that the first one was hex-based or hexadecimal and the second one was not. I guess it could be. We wouldn't know, yeah. Our second B, there it is. That one was a lot easier than the third one. The third one was pretty diabolical, like, having a container with no shell. But more on that
I'm
tomorrow.
going to say, when I put them together, challenge number 3 was the first one I put together, and I could see quite a lot of people that I tried it out on struggling a little bit. So if you're out there struggling, you are not alone. And so challenge 2 was intended to be a little bit more straightforward. And hopefully it gives you some ideas around what people can do with BPF tool, looking at maps, looking at programs. And yeah, it's kind of fun. So I think, well, Duffy already mentioned that we already pre-recorded the solution for challenge 3. Took us a little bit longer. It was a bit more involved.
Yeah.
And if you're interested to see how to solve challenge number 3, it will be streamed out tomorrow in our YouTube show called Echo, which stands for EBPF and Cilium Office Hours, kinda. And it's episode 64 tomorrow. So there's a link there, isogo.2/echo64. Or you could just subscribe to the YouTube channel you're watching this on, and then you'll automatically get notified, I guess, by YouTube when that gets streamed out tomorrow. So I think it just remains for me to say thank you so much, Duffy, for participating in the CTF challenge and solving it with me today. And I hope everybody enjoyed it.
All right, everyone. Now we're going to be moving into the next section, eBPF programming and internals. The next set of talks are going to be, talks about people sharing their perspective and their experiences with writing eBPF and how that's going for them. The first talk we have is Falco's discovery of the modern eBPF world, and it's by Andrea and Jason. Welcome.
Hello everyone, and welcome to this session. We're going to talk about Falco's discovery of the modern eBPF world. I'm Jason, an open source engineer at Sysdig and a core maintainer of Falco.
Hi all, nice to meet you. I'm Andrea Terzolo, a research fellow at Polytechnic of Turin and a core maintainer of the Falco project.
So, first of all, what is Falco? Falco is a cloud-native runtime security tool incubated by the CNCF. Falco monitors everything happening in your system and sends you an alert when suspicious activity is detected. This happens by instrumenting the kernel and collecting events generated from your system. And although Falco is dramatically expanding its use cases in the space of cloud security, its main focus still remains container and endpoint security. In Falco, kernel instrumentation happens with either a kernel module or an eBPF probe. Falco is an early adopter of eBPF. It provides a safer alternative to the kernel module and also helps with system compatibility, especially in environments where kernel modules are not an option. eBPF also has visibility over a high number of kernel events, which is exactly what Falco needs. However, all that glitters is not gold. There are indeed some pain points with our current eBPF probe. First, it's very hard to guarantee portability across many compiler and kernel versions. To mitigate compilation issues, we provide a high number of pre-built probes for many kernel versions, but that's quite expensive in terms of storage and can't possibly cover all cases. Plus, this doesn't save us from battling with the kernel verifier every now and then. Also, our code is not uniform. eBPF is gaining many interesting features, but those are not available in all kernel versions that Falco supports. So we are forced to either not adopt those features or enable them only on some kernel versions. This makes performance and compatibility quite unpredictable and also makes the code bigger in size and harder to maintain. So what can we do? Should we go for Curry? Well, maybe yes, because Curry definitely will help with our portability problem. However, that will not be enough to solve our uniformity and code size issues. Should we start using the newest eBPF helpers and tools? Sounds great on paper, but then supporting older kernels will become even more troublesome. So maybe we should rewrite everything from scratch? This sounds like a joke, but it's actually a good solution. Let me explain. We can keep our current eBPF probe for supporting older kernel versions and also have a new probe for only the newest kernels that will benefit from the latest cutting-edge eBPF features. Sounds like tons of work, but also a win-win situation. So that's exactly what we did. As you can see in the picture, the new eBPF probe will not substitute the old one. Instead, the two are meant to complement each other. The old one will be the best option for old kernel versions and will benefit from a limited set of eBPF features, whereas the new probe will leverage eBPF at its state-of-the-art, but will target kernel 5.8 as the minimum supported version. That's the idea, and now Andrea will go through some of the details.
Thank you, Jason, for this exhaustive introduction. Now, let's dive into the new eBPF features. First of all, to trace the whole system, we have to send a lot of information to user space. But what is the best way to push a high throughput of data with BPF? Today, there are two main approaches, the BPF perf buffer and the BPF ferring buffer. Let's start talking about the perf buffer. In this case, we have just one API to send data, the BPF perf event output. The main disadvantage of this helper is that we cannot push data directly into the buffer. We first need to store them into an auxiliary BPF map. Moreover, when we try to copy the content of the map into the buffer, we have to discard all the data if the buffer is full, wasting a lot of precious clock cycles. The ring buffer, on the other side, provides us with a new reservation approach. The BPF ring buff submit API allows us to reserve space directly into the buffer, avoiding any extra memory copy. But this is not the only good news. If we try to reserve the space and the buffer is full, we can interrupt the execution flow without collecting any data. All this sounds amazing, doesn't it? Yeah, but there is an hidden downside. To use this reservation approach, we need to know the data size at compile time, and this is not always possible. For example, there are cases in which we need to extract a file path from a syscall, and we cannot know its size in advance. So, does it mean that we cannot use the ring buffer? No, luckily the ring buffer provides us with an API equivalent to the perf buffer one. This API is called BPF ring buff output, and we can use it when we have variable size data to send. This ends our discussion on the user kernel communication. Now let's go to the next feature. As you can see from the title, here we talk about BPF type format, also called BTF, so the debug information for BPF. The cool thing about this new type format is that the verifier can use it to perform small checks on loaded programs, allowing us to write simple and more efficient code. By the way, not all programs can take advantage of this format, so the BPF tracing ecosystem introduced a new program type to do it, the so-called BPF prog type tracing. These programs can directly read kernel user memory without helpers like the BPF prog read. But let's see what does it mean with a concrete example. Let's start considering the trace point we use in the old probe, the BPF prog type raw trace point. In this simple program, we need to access the file struct pointer from the current task, and since we cannot take advantage of BTF, we have to use the standard BPF readInt macro. The code seems really simple, but looking at the bytecode, we can see that we have 19 instructions for just 5 lines of codes. Let's see if we can do better with BPF prog type tracing. As you can notice, the code is quite similar to the previous case. It's only a little bit easier because by exploiting BTF, we can directly difference the task pointer. So, coming back to the bytecode, we can see that this time we have just 6 instructions. So, for sure BTF allows us to improve performance because we reduce the bytecode size, but it improves also the code readability and maintainability, since we obtain a simple C-like code. This ends our discussion about programs. Now, let's see what's new in BPF maps. The BPF global variables can be seen as a particular type of map. They are essentially an array with just one key value pair that contains all global data. To better understand it, let's see an example. If we define 6 uninitialized BPF global variables called global1, global2, and so on, we will obtain an array map like this, one single entry that contains all our variables. The cool thing is that BPF programs can access the right offset in this data blob without using any BPF helper. This is very important because it brings a concrete performance boost when we have to configure our programs. Moreover, also the user space can benefit from this feature, since global variables are memory mapped, and so we can access them without the BPF syscall. This last topic ends the review of BPF new features. Now let's see how we can take advantage of all of them in the modern probe architecture. To compare the design choices of the modern probe with the old one, we will consider the syscall capture flow, because it is linear and easy to understand. More precisely, we will consider the sysenter case, but the sysexit one has exactly the same behavior. Let's start with modern architecture. Every time we have a new syscall, our sysenter trace point is triggered. This program is of type tracing, so as we said, we can take advantage of direct memory access. The first thing we want to do inside our sysenter program is to filter out not interesting syscall. Please note the sysenter program is called for every single syscall, even if we are not interested in it. And this, unfortunately, could have a bad impact on our performance. So, the rationale here is to filter out syscall as soon as possible. The good news is that thanks to global variables and BTF-enabled programs, we are able to do it without calling any BPF helpers. Unfortunately, we cannot say the same thing for the old probe, where we have to call at least 3 helpers before reaching the filter logic. Now, let's focus on what happens after the tail call. In the modern probe, thanks to direct memory access and 2 extended prog sites, we are able to collect data and push them to user space in just one BPF program. While, as you can notice in the old probe, we need at least 2 different programs, one for collecting data and the other for sending them. Another important difference is how we send data to user space. In the modern probe, we use the ring buffer approach, so we send fixed size events through the reserve mechanism, while for variable size ones, we use the output API, and so an extra memory copy. On the other side, in the old probe, we are obliged to copy every single event twice before sending it, because the perf buffer doesn't offer any reserve approach. These are some of the most interesting high-level benefits that we can gain from the modern BPF features, but as you may imagine, there are many other minor advantages that we have no time to analyze here.
At this point, it's time to find out how the new EBPF probe performs. Let's start by saying that it's very hard to measure the performance of kernel instrumentation. The most reliable way we experimented is to take measurements at both the user space and the kernel level, and then see if the numbers collected on both sides make some sense. On a user space level, we run a benchmarking application with and without our EBPF instrumentation injected in the kernel, and then observe how much the benchmark performance changes. In this case, we use Redis benchmark, which we thought could simulate a realistic use case for a well-known cloud application. For kernel-level measurements, we have been a little more creative. we developed a little tool that hooks into the EBPF syscall enter and exit trace points, just like our probe. By inserting a hook before and after the programs of our probe, we're able to measure the time difference and collect samples. So in this way, we're able to measure the bare kernel execution time of each syscall with and without the probe. And although this may not be super precise, it gives us a good estimate of the kernel slowdown we introduce. The same measurement method has been used on the old probe as well, so that we compare the difference between the new and the old one. And here you can see the results of our experiment. The new probe has about 40% less overhead on syscall execution compared to the old one. Also, Redis benchmark slows down by about 5% with the new probe and 8% with the old one. So we have a 3% performance improvement on the benchmark and about a 40% speed up on the instrumentation overhead, which gladly confirms the numbers we collected at the kernel level. At this point, we also decided to run the user space benchmark with our kernel module instrumentation to see how the two eBPF probes compare. The kernel module introduced an overhead on the benchmark about 20% lower compared to the new probe and about 45% lower compared to the old one. Sadly, this shows that eBPF is still no match for the kernel module performance-wise, but that accounts to only 1.2% performance difference on the benchmark, so the difference between the two is getting far less visible on real use cases. Plus, we think that improvements from the old eBPF probe are still very interesting.
As a final step, I would share some takeaways I learned during this adventure. The first one is don't be scared by the old BPF development. There was a radical change in the effort required to write BPF application. Implementing a feature in the old probe with restricted proc size, loop unrolling, and ambiguous verifier log could require some days, but thanks to all the modern features and to verifier everyday smarter, you can easily develop your application without losing a few years of life. Another key point is the testing phase. Even if we are talking about BPF, you can always find something to test. For example, in the model probe, we used libpf and Google Test to assert every single event that our BPF program sent to user space. And this really helped us a lot to spot tons of bugs. The last point probably sounds stupid, but it helps me a lot during the development. Writing BPF program is not like writing C programs. This is probably one of the worst errors we have done in the old probe. We have tons of inline methods just to reuse the same few line of codes. In my opinion, sometimes it's better to duplicate code to keep the flow linear. You must never forget that we need to help our little friend verifier to understand what's going on. I hope this suggestion could help you during your BPF travel, but now I think it's time to close. I hope that you were able to easily follow us, and if you have any doubt or any curiosity, please feel free to reach us on the Slack channel. Bye and thank you.
Thank you very much. That was a great presentation on actually leveraging BPF or comparing that to the KMod model that Sysdig uses. And that's actually pretty great. Our next talk is Metalens, live programming and visualizing eBPF. And it is brought to us by Nikita. Thank you, Nikita.
Hello, my name is Nikita. I'm an open source developer from Scotland, and today I'd like to talk to you about bringing new higher levels of abstractions to eBPF. So we already have lots of great existing tools like BPF Trace or libbpf, and we often use them to create our own tools based on BPF with applications in observability, network engineering, and well, you name it. But in my mind, the problem with these tools is that they are really hard for someone who is just starting with low-level programming, or even for someone who already has lots of experience in Linux. And I'm speaking from my personal experience here because it's very challenging to start writing BPF programs. You need to take care of both the user space and kernel space programs, and even if you're using BPF Trace, as great as this tool is, it can be non-intuitive in many ways, not in the least because it's mostly a command line utility. And command line tools have served us well over many decades, but they are not using the full power that the modern technologies give us. So, for example, you cannot do more interesting visualizations in the command line, and the interaction usually happens through text only, leaving graphics and input devices such as a mouse unused. But there's also the factor of the sheer complexity of low-level languages. So what I would like to discuss here is the idea of taking inspiration from databases. With traditional database systems, we can make quite sophisticated queries without writing much code besides SQL, which can be seen as another API or another layer of abstraction on top of a typical database system. So, for example, when we write database queries, we don't go over such minute details like reading files from a disk. We don't even think in terms of loops or conditionals. We are just describing what is the result we would like to get, and not how exactly to obtain this result. This part is usually for a database system to figure out. So this gives us an interesting idea. Why don't we try to see the Linux kernel itself as a sort of a database, which will provide us with all kinds of information about the state of the system? But the problem with this idea is that when we work with databases, we think about the data as something static, while in the case of the Linux kernel, we deal with millions of events which happen every second. In the database world, this problem is usually solved with streaming systems like Apache Spark or Flink. And in those systems, instead of asking questions about stored data, we store the questions themselves and pass the dynamic data streams through them. And as a result, we can filter or transform this data using the familiar SQL language constructs, and then collect and analyze this data however we want. One advantage of such systems is that the data stream can be unbounded, meaning that it has no start and it really has no end, so it's practically infinite and spontaneous. And the streaming system can run queries over very long periods of time, which sounds quite similar to what we do with the Linux events tracing. So we can try to take inspiration from streaming systems as well. But of course, we have another slight problem with this idea. Like, how do we deal with millions of events? How do we source these data points from the kernel and filter or aggregate them? Well, we don't need to think much about it because, of course, we have eBPF. And we can compile queries down to BPF code and execute it at the point where these events happen inside the kernel. And as a concrete example, let's construct a very simple SQL-like query, which will count a number of system calls made by all processes in the system. And in this case, we are interested in system calls with the ID 1, which correspond to the open syscall. And once we execute this query, it will automatically attach the resulting BPF program to the kernel probe, and it will start gathering and displaying results. So how this works is basically this query is broken down into multiple simple operators, starting with the print, which requests the data from the aggregate operator, which in turn requests the filter data, and in the end it goes down to the kernel probe, which sources data from the kernel and sends it back upwards. And once we have that, we can compile each operator into efficient BPF code, which will take care of both the user space and kernel space for us. And we don't even need to care about the verifier in this case. On this slide, you can see some Python pseudocode, and each line of this code is translated from the operators on the left side. And what's interesting here is that operators can be used to generate data structures in addition to code. So as you can see, the aggregate operator has created a separate BPF map for us to transfer the data to the user space, so we don't need to spend time thinking about it. What we have seen so far doesn't look very different from BPF trace, though. It's more like just a different flavor of syntax. But in fact, there is actually an important distinction here, because we put the data at the forefront, and that makes us think in a different way about those programs. Like in the case of BPF trace, we mostly write code in the imperative style, while SQL and the streaming abstractions make you think more in terms of the declarative style of programming. And this, the declarative style gives us an option of presenting it in a visual way. So for each operator in the SQL query, we can introduce a corresponding visual block. These visual blocks can be connected and composed in an intuitive way, making a kind of a graph that shows the flow of the data from top to bottom. And first we have data sources like the kernel or user probes, and we have data sinks which will display the data or send it further, like to a logging server or a database or a file. It's basically for you to choose. And between the data sources and sinks, we can manipulate the data in the stream. We can filter it, aggregate it, or combine it from multiple data sources. We basically can do whatever we want with it. And this approach helps us to see the flow of the data. And once we move into the realm of visual representation, we can start doing some really interesting things with it, like live programming. And what this means is that you will be able to see the immediate feedback after changing the properties of each visual block. So once we change the process name in the filter, for example, the program will be automatically recompiled and you will start to get new results. This is more similar to the reactive style of programming, which you can find in things like spreadsheets, where you can dynamically change cells and the entire sheet will be recomputed immediately. The interesting part here is that because we have complete information about the program, we can also build the runtime dependency graph, which can include data that is gathered from sources other than the kernel and eBPF. It doesn't even have to be a single machine or a single container. So if we combine and compose these visual blocks, we can build quite complex systems and programs this way. So for example, let's take a look at the program on this slide. Here we are first waiting for an event that comes from our distributed tracing system that can use something like the OpenTelemetry API. And in this case, this can be a trigger for an event like an HTTP request. And it also, the HTTP requests come with some context information about the request, which we can use later. Next, we can also gather some events from an eBPF probe, and in this case, we are interested in a number of memory allocations that happen within the span of and within the context of the HTTP request. And the compiler and the execution engine will automatically figure out the correct order of events. So in this case, the memory allocations will be collected only after the HTTP request event is triggered. And since we have the context information from the tracing system, we can also filter events by the target HTTP endpoint or any other information from the HTTP headers. In this particular case, we are interested only in events that happen within requests to the login page of a web application. And finally, at the last step, we collect the size of a memory allocation from the kernel event, and log the results to a file. And of course, we can also send them forward to the same distributed tracing system or to a database of your choice or to a file. Well, you get it. And as you might have noticed, we also use formulas here to describe the kind of data we are interested in. This is pretty similar to how the formulas work in spreadsheets, where you can refer to other cells. And in this case, you can refer to other visual blocks too. And the system here is very flexible. We can split the data into several substreams, where one stream can go into the logging block, and another can feed into a block that will, for example, count the number of allocations or find an average size of an allocation. And it doesn't have to be just text either, because we can also feed data into a chart or a histogram or any other kind of visualization block, which you can also fine tune and choose dynamically depending on the flavor of your data. So ultimately, this system could become kind of a universal toolset supporting data sources like distributed tracing systems and telemetry, or function calls from multiple languages, from multiple language runtimes, or streaming databases. And all these data sources can be combined in multiple ways and synchronized to work together in a single system. So these examples that you have seen work in a web browser, using a WebSocket connection to transfer data in real time. So once you have constructed your program from these visual building blocks, we can send the entire program to the server where it is compiled down to eBPF code, and it is immediately executed. This way, the visual representation of a program becomes a kind of a zero-cost abstraction, so it makes no difference. It looks no different to a similar program that you might have written yourself. And the execution engine takes care of attaching to user probes or kernel probes, and it's communicating between the user space and the kernel space using eBPF maps, which can be very efficient, especially in the case of special kinds of maps like ring buffers. So basically, we can transfer the data from eBPF maps into WebSocket almost immediately, and then this data can be displayed and rendered and handled by JavaScript. And for the most part, as a user, you don't even need to care about all this. But if you would like to implement your own operators, you can do so by extending the compiler, which is written in Rust. So you can introduce your own data sources, data sinks, or other new functions. And of course, this approach is not ideal, and with the complex scenarios, you would probably still opt for writing your program using libbpf or other proven production tools. But an important point here is that you will be able to use existing scripts and programs by embedding them as separate visual blocks into your pipeline. And it can work the other way around too, like you can call programs you build in this visual style from your existing tools or apps. This visual approach also has several important advantages over command line tools. So for example, it's more amenable to loading and showing more debug information. So for example, when you switch the debug mode on, you will be able to immediately see what kinds of data you get in each of the visual blocks and what kind of data pass through your pipeline. I think another important part of this is that it's not only a visual interface, but more like an integrated development environment with features like code highlighting and code completion. And recent advancements in eBPF, such as BDF, which provides type information about structures, can definitely help with that. And well, at this level of abstraction, it's also easier to optimize programs because the compiler can construct ad hoc data structures to transfer data from BPF programs more efficiently. So, in conclusion, we have talked about an alternative way of thinking about BPF programs. And this approach is certainly not a replacement for writing code in complex scenarios, but in many cases, I think it can provide a simple and fun solution to the problem of complexity, because personally, I sometimes struggle with some parts of writing code for BPF, like dealing with the verifier or thinking about the kernel side of things. It's all very tricky. And this project is currently in the very experimental alpha stage, and it's under heavy development, but it's open source, and you can find the source code at the GitHub page you can see on the slide and try it yourself. And that's all for me. Thank you very much for your attention, and I will be available on Slack to answer your questions. Thank you.
Awesome work, Nikita. Thank you very much for sharing that. It looks like a really interesting querying tool around how this was work. As I was watching this with Liz, one of the things Liz brought up was that it looks a little bit like OS query, right? Because you have a bunch of data that you can kind of arbitrarily search. I think it looks like a pretty interesting way to go about it. I think I'd love to have Nikita on for an Echo office hours to explore this tool a bit more. But that'd be fun. Our next talk is peeking into the eBPF verifier with Sheng Shui.
Hi, welcome to this talk about peeking into the EBPF verifier. I'm Sheng-Si Yu and I work at SUSE as a kernel engineer. So let's begin. What is the verifier? Well, the verifier is what stands between our BPF program and the deep dark chasen of destruction. When eBPF programs are being loaded, the verifier will check the program to see if they're safe. If they're not, the program will be rejected and can never run. But how does the verifier work? The verifier works by checking the type and value used in the program. Let's see an example. Here we have an eBPF program. The return value should be an integer and we return 0. And since the type of 0 is indeed integer, this program will pass the verifier. Now, if we have another program that returns the socket buffer pointer instead of 0, the verifier will reject because an integer is not the same type as socket buffer pointer. But before the verifier can reject our code, the compiler will usually first complain. So why do we need the verifier when we already have compilers? The reason is that compilers trust the user too much. To see what I mean, let's look at the same code, but this time, we can cast the socket buffer pointer too long. And in this case, the compiler will no longer complain. But you give it to the verifier. The verifier will still reject this code. And that is because the verifier sees things vastly differently from the compiler. The verifier does not see all the types we wrote. Instead, the verifier has its own type system. And in this case, it will infer from the ground up that skb is pointer to context, which is not the same type as scalar, and thus reject the program. So far, we've only covered how type checks. But what about values? Well, to see how value checking works, let's look at another example. Here, we are accessing an array, ARR, using an unsigned integer I as the offset. The verifier will actually reject this program, and this usually caught newcomers off guard. So why does the verifier reject this code? Well, the reason is that the verifier is very pessimistic. Just as people can see half cup of water differently, the verifier and the compiler also sees array access very differently. The compiler will lean toward the access being with bound, while the verifier will lean toward the access being out of bound. But the verifier is not drawing that conclusion out of thin air. The way the verifier reasons is like this. It sees that I is externally initialized. So it reasons that I can just be any unsigned integer value, which means I can be a value between 0 and 2 to the 32 minus 1. Now, if you try to do array access using 2 to the 32 minus 1, it will be out of bound, and therefore the verifier rejects this code. To make the verifier happy, we can use if statement to trim down the possible value of I. Here's how that works. At first, the verifier still thinks that I can be any value between 0 and 2 to the 32 minus 1. But inside the if statement, it can reason that since I is less than or equal to 3, I can only be a value between 0 and 3. In this way, it can be sure that array access with I is always within bound, and therefore the program is safe. The same thing can be done in a different way with bitwise AND and a mask. The verifier will still come to the same conclusion that the access is safe. Now, I need to make a small confession though. What I've said so far is not really how the verifier works. The verifier deals with low-level details called bytecodes and register. But conceptually, it's close enough. So instead of variable I2, the verifier deals with register R2, which is where the variable I2 is stored. And in that way, the verifier checks the type and value of eBPF program to make sure they're safe. Thank you for listening. You can check out the slides for additional links to resources if you're interested.
Awesome. Well, thank you very much for that talk. That was a great chat talking about the challenge, or taking a look at how the eBPF verifier looks. Our next talk is very similar. It's fighting and overcoming the complexity limit, which is enforced by the verifier. And this talk is by Daniel. So welcome, Daniel.
Hello, future viewers. Welcome to my lightning talk on fighting and overcoming the complexity limit. Another way you can title this talk is using a verifier-friendly algorithm. The agenda is pretty straightforward. I'm more or less going to go over a chronology of events while pointing out along the way some interesting tidbits. For context, I've been working on a project called microsegmentation. You don't need to know too much about what microsegmentation is, other than that it's more or less an applied form of packet classification, where packet classification is the traditional networking research topic, at least one of them. The problem statement in this case is that we receive packets off the network, and then we want to categorize these packets into user-specified flows. Once we have a flow associated with the packet, we want to take some kind of user-configured action, for example, drop the packet, reroute it, etc., etc. Another important thing to point out is that we are currently on the 5.4 kernel, meaning that it's not too old, but it's also not the newest kernel, so we can't take advantage of the latest upstream kernel features. I'm sure anyone who's worked in depth with BPF before has experienced this kind of pain where you have to be waiting for kernel upgrades to use the latest and greatest features. So here's the first pass at the BPF code I wrote for microseg. There's a lot more code than this, but the loop is where all the complexity is contained, so I've decided to focus on that for this slide and the rest of the slides in this presentation. As you can see, the algorithm is pretty explicit. It's pretty simple. Essentially, we're walking over an array of policies, and then we try to match the packet against each policy. As soon as we find a match, we bail out and return the requested action code. This worked pretty okay as a prototype. It was functional, but as you'll see in the next slide, things start to get a bit hairy once we start to add more features. So at this point, there's a lot more complexity in the body of the loop, as you can tell. It turns out the verifier really does not like control flow in the body of the loop. From what I could gather, every time something like continue is inserted into the body loop, the number of states the verifier had to explore would double. So we really quickly hit the complexity limits the verifier imposes, which is 1 million instructions explored. To get around this limit, we had to start spreading out policy processing between multiple tail calls. However, the downside to that on the 5.4 kernel is that you can no longer mix tail calls with BPF to BPF calls, meaning that all the helper functions that you see in this function had to be inlined. What this means is that instead of the match function being verified once per loop iteration, it was being verified 4 times, which had really disastrous impacts on the scalability or the complexity limit. It was painfully obvious by this point that the current implementation would not scale. For example, we could barely get to 256 policies/rules, let alone the deep thousands that we were aiming for. On top of that, overhead, even at 64 rules, where we're matching the 64th rule and the first 63 are just duds, the overhead was way too high. We were dropping network throughput from 12 gigabits a second to 8 gigabits a second, which is pretty much unacceptable. A lot of that had to do with the fact that we're doing 8 tail calls, 8 rules per tail call, and reparsing the packet for each tail call. So we had to get rid of that somehow as well. Fortunately, there's a large body of theory behind packet classification, which I wasn't aware of until now. So we did some literature review. So it took a good bit of searching, but I eventually found this paper that was really relevant to the problems we were having. That's the first bullet point. The premise of the paper is pretty much how to implement IP tables using BPF, along with some pretty nifty techniques that I'll go into in the next slide. The second bullet point is a book that I found super helpful. It's called Network Algorithmics, and it contains a lot of really fancy algorithms that are distilled into just a few pages. I've learned a lot of interesting things from just skimming the book when I wake up in the mornings or whatever. So highly recommend that. So both the paper and the book in the previous slide both go into pretty good depth about this algorithm called linear bit vector search. The basic idea, and I'll lay it out pretty briefly here, you can read this slide more in depth if you want, is that we're going to decompose a packet into a bunch of dimensions, and for each dimension we can do a lookup from a map that returns us a bit vector. Once we have like n bit vectors, we can do bitwise arithmetic over all the bit vectors. So for example, if we have bit vector for source IP and a bit vector for dest IP, and you bitwise AND them, the resulting bit vector tells us all the policies that match the source and dest. Once we have this final bit vector, we can do U64 size strides over the final bit vector to identify non-zero U64. What this means is we can basically process 64 policies at once in just a handful of machine instructions, meaning that the fast path is really, really fast. And then you can do this really neat little trick at the end once you have the final U64 and find the first set bit using something called a Debugging sequence. So on top of being a pretty elegant algorithm, at least in my opinion, LBVS is verifier friendly because the body of the loop is really tight and there's minimal control flow, as you'll see in the next slide. It's also super cache friendly because we're doing straight line data access. So the hardware prefetcher can prefetch pretty accurately. It's also super CPU friendly because modern CPUs can tear through word-sized logical operations. So all this combined means that we have a really fast algorithm despite the fact that it's a linear algorithm. So here's the third pass and the full rewrite of the BPF portion of microseg. The top half of this code snippet is the bit vector lookups. It's just 2 of them here. There's multiple, like I mentioned before, 1 for each dimension of the packet that we care about. Once you have all the bit vectors, then you do the linear search portion of the algorithm, and that's the loop that I'm showing here. Pretty much you're doing word-sized strides over all the bit vectors and doing some kind of arithmetic operations. The logic is kind of convoluted here because a lot of it has to do with our product requirements, but hopefully you get the idea. A cool thing is that when you disassemble this loop body, it's actually not that many instructions because we're just doing some very basic word-sized data accesses and some arithmetic operations. The outcome of such a fancy algorithm is that we have finally reached baseline performance, meaning that when you have microseg on, there's actually no visible performance impact because the bottleneck has presumably moved somewhere else. This algorithm scales to 2,000 plus rules in a single tail call, meaning it's super, super efficient, at least on the verifier front of things. The downside, however, is that it's quite a complicated algorithm, and you have to really understand the algorithm before you can make any code changes. Like you can't just read the code and figure out what's going on. That's going to be more or less impossible. And that's it. Thanks for watching.
All right, that was another great presentation talking about the complexity of rules and actually how they were chasing that particular problem there at Aviatrix. Really interesting chat. The next talk is porting eBPF compile once run everywhere to ARM64 leads to fix. I'm sorry, no, it is not. It is building an oomkill-exporter powered by eBPF. Thank you, Christian, for presenting.
Hello everyone, my name is Christian Fekete and I will show you how you can build an eBPF-based oomkill-exporter in 5 minutes. I'm currently working at solo.io and I was at LastPass before that. Let's start with a very quick summary of what oomkills are. As you may have already known, the origins of the oomkills dates back to the old days of Linux. When your machine, that can be a bare metal machine, virtual machine, or a node in the Kubernetes world is running low on memory, older pages of memory will be reclaimed. If this is not possible, a function called out of memory will be called with a single task, avoid running out of memory. This will first check the available swap, then check when was the first attempt to free memory pages, maybe even wait for pending IO operations to finish. Before hope is lost, it will have to kill a processor. In the case of Kubernetes, the basics mentioned above still apply, but now you can leverage quality of service classes for your plots. For example, guaranteed, burstable, and best effort. Behind the scenes, these are translated to a score, and that score can help determine which process should be killed. In most of the cases, pod gets killed if it reaches the limits of its containers. So yes, you should always configure these, or the node of the pod gets overcommitted. Monitoring these events is crucial for reliability, but catching them is not trivial. Fortunately, eBPF can help. We will take an existing oomkill detector script, then use Bumblebee to deploy it in a Kubernetes cluster and expose these events that it captures as Prometheus metrics. Okay, so let's see this in action. We will use the BCC repositories oomkill.bpf.c example. That's all the logic that you need to capture the oomkill events. And with this approach, you would need to use another C file to handle the lifecycle of the BPF code, but with Bumblebee you won't need this. Let's take a look at the differences between the upstream oomkill logic and our BPF logic. First, we have abstract, that is currently changed here. Here we are essentially have a map that can be written from both kernel and user land, and we are migrating it from per buffer to ring buffer. We have to do this because Bumblebee currently only supports ring buffer and hash map, but this is currently a best practice for fairly new kernel versions because ring buffer saw suboptimal performance and tedious tasks during BPF development. Then secondly, we are changing our core BPF logic, which is basically being triggered by every oomkill process kernel probe. We are already enjoying the benefits of the previous migration as we can leverage the reserve commit API of ring buffer. With this approach, you can reserve the space for the data early on and avoid inefficient use of memory, because if you could reserve the memory for your sample, the commit to user space cannot fail. We can use Bumblebee to build this into an image. I have the BE CLI up and running here. The comments are similar to what we have with Docker. To build, you can use BE build to build this logic into an OCI image and push it into a local or remote registry. I have one running locally, so I will use that. After you build it, you can push it to this registry, and after that you can run it. If you can successfully run it, that means that it passed the kernel verifier, so your code should be safe in the kernel. I deployed the CLI package as a daemon set on every node. I have 3 nodes in this Kubernetes cluster, and Bumblebee is running on all of that. And I also have a memory leaker program that is currently in crash rollback because of the oomkill sessions. If you check the Prometheus UI, we can already see that we have this metric exposed, and we have the same labels that we used for our struct in the BPF code. We are currently working on tighter Kubernetes integration. We will have probes like this to deploy your custom BPF logic, and we will also have better correlation to pods for your actual processes. So as you can see, it's this easy to take an existing libBPF script and package it with Bumblebee and expose the output Prometheus metrics. The possibilities are almost endless because now you have an easy way to get familiar with BPF and package your logic as OCI images. Thank you for joining me today, and I'm available on Slack for Q&A.
Awesome talk. That was a really fun one, talking about the oomkill-exporter, powered by eBPF by Christian. Our next chat is porting eBPF core to ARM64 leads to the Fix the Kernel by Francis. Welcome.
Hi everyone, my name is Francis Daniel, and today I will present you how porting an eBPF core tool to ARM64 led to fix a bug in the kernel. In my work, I use BPF2Go. According to the project README, BPF2Go enables you to compile a C source file into eBPF bytecode and then emits a Go file containing the eBPF. So, BPF2Go permits you to call eBPF code from Golang executable. By calling internally Clang, BPF2Go can generate eBPF bytecode for several architectures, among others AMD64 and ARM64. In the remaining of this presentation, we will focus on the ARM64 architecture. In my case, I wanted to port Inspector Gadget to ARM64. Inspector Gadget is a set of eBPF tools which can be used to monitor and debug a Kubernetes cluster. First, I generated the eBPF bytecode using BPF2Go. Then, I cross-built our container image with Docker buildx. Finally, I ran our integration test and realized some gadgets were not working. Indeed, the trace exec gadget, which monitored the call to the execv syscall family done on your cluster, printed nothing. More particularly, the eBPF code linked to syscall enter execv was executed, but not the one linked to syscall exit execv. As a consequence, I built an ARM64 kernel, ran through QEMU, and attached GDB to it to trace what was happening. On the middle of the screen, you can see the kernel call stack when you, for example, run ls from bash. As bash calls exec, you first enter into the kernel in the execv syscall. Then, you will jump into do execv at command, kernel function. As ls is a binary executable, the exec bin prm function is called. Since ls executable format is elf, the load elf binary function is called. This function contains the macro start thread, which is defined for each architecture. In the case of ARM64, this macro expands to start thread. This function in turn called start thread command. In this function specific to ARM64 architecture, the forget syscall function is called. This function sets the ARM64 register containing the syscall number to an invalid value. As a consequence, the tracing of the syscall exit cannot occur because print syscall exit checks the syscall number and nothing will be reported as it is invalid. The upstream fix mainly consists in not forgetting the syscall number and remembering about it after setting all the registers to 0 as a new thread is about to start. For non-upstream kernel, a workaround was written by using kprobe. This workaround permits running exec-snoop and trace exec on all kernel, but the command argument will not be reported. For example, when you run ls-al, exec-snoop will print ls but not -al, contrary to the normal behavior. As a conclusion, a kernel bug was fixed upstream. Note that this bug was backported to all stable kernels. So, you can now trace execv syscall family on ARM64 hardware. Also, Inspector Gadget was ported to ARM64. In the future, we plan to test the ARM64 port of Inspector Gadget to several platforms to be able to catch particularly specific bugs. I would also like to thank Jeremy Piotrowski for his help finding this kernel bug. I thank you a lot for your attention and feel free to ping me in the chat if you have any question.
Thank you, Francis. It's really interesting to see how the type data might change between different kernel architectures. That's a really great chat. Our next one is the power of a self-describing kernel, how BTF can benefit applications. And this is by Alan and Stephen Brennan. One other thing I'd like to say is that it's really great to see all of the interactive questions and in the threads for each talk. It's really making it a very interactive thing. And thank you so much for asking all those questions and making people feel welcome and a part of the show.
All right, so Alan and I are going to discuss two different ways that BTF can really help modernize common workflows. First, kernel debugging, and then Alan is going to describe how it can help with packet capturing. So if you've done any kernel debugging before, you probably, or at least interactive debugging, you're familiar with a lot of options. There's probably KDB and KGDB, which are built into the kernel. You have the set of GDB-based debuggers and the extensions for kernel debugging. And then finally, you have independent debuggers like Tetragon, which is built on Python scripting. And all of these are great, and they all have a requirement for debug symbols, except for KDB. The reason for that is that KDB can benefit from some of the built-in information in the kernel, like KLSIMs. So right now, we have at least three really important pieces that help that could help debuggers work. We have KLSIMs, a symbol table which contains information about the offsets and names of all sorts of symbols in the kernel. And most distribution kernels enable KLSIMs all, which means that we include not just function information, but also variables from all different sections of the kernel. Second is ORC, a stack unwinding format. In case you don't use frame pointers, you need a way to figure out where each stack frame ends. And this is roughly similar to Dwarf CFI, but built explicitly for the kernel. And then finally, we have BTF, which enables really all of the other features of a debugger because it can describe C types, such as the struct layout, the member name, things like that. And this is essentially similar to the Dwarf debug type information. So our goal is to take these different self-describing components together and merge them and allow basic debugging tasks to happen without even referring to an external Dwarf file. So this would enable things like Dragon or GDB to debug a live running kernel via proc kcore, or a core dump triggered during a panic, maybe, without needing to open, a symbol table in an ELF file without looking for those Dwarf information. But of course, we're not trying to replace all features of Dwarf. There are a lot of really detailed, lots of really good data that Dwarf can give you, like source code mapping, and the kernel just doesn't have space for all of that. So these are just the core features we need. So the steps to get this all working, we've got at least three work streams going on. First, KLSIM symbol data wasn't able to be found in a core dump, and as of Linux 6.0, this is resolved. We record where the symbol table is inside of the VM core info node. So if you load a crash dump, you can find that symbol table and start parsing it. Second, BTF data currently only uses or has data for function and per CPU types, but we've got a work in progress series to address this by generating all types. And then last, no debugger yet understands BTF or KLSIMs, but we're working on upstream branches for Dragon to add support for that. And next, Alan's going to tell us a little bit about packet capturing.
So if you've used Wireshark or TCP dump, you're probably familiar with capturing network traffic, and that happens at specific tap points in the kernel. But funnily enough, the BPF type format can help here as well. So with eBPF, we can be a little bit more flexible. So having that type format information can tell us about kernel functions and what arguments they have. And using that information, we can then identify the functions that have an SK buff, which is the network metadata data structure. And if we know which functions have one of them, we know we can gather tracing information from those functions as well. So in this case, the user is specifying a function name as a device, and because we have BTF, we can then go and take that function name and figure out if it has one of those skbuff arguments and which argument it is. So for example, here we're running TCP dump on a kernel function. This is the function to scan Wi-Fi. And importantly, we have to specify link type here because we don't have, unless, you know, by default it's going to be Ethernet, but for a lot of kernel functions, we might be higher up in the stack before the Ethernet frame is being prepended, or you might be somewhere else like in the Wi-Fi stack. So we need to specify which type of link we're dealing with here. We can't just assume we're dealing with Ethernet. So if those changes are made in libpcap, then Wireshark and TCP dump can take advantage of that, and we can sort of have a much more flexible way of capturing packets, which can be very helpful for kernel debugging. So in summary, kernel debugging and packet capture are things that we've kind of been doing for forever, really. But with BTF availability, we can see there's new possibilities. For debugging, we don't need to rely on expensive external type information when we're doing simple debugging tasks. And we can simplify other tasks as well. So packet capture at arbitrary functions becomes simpler because we don't need to specify any details about the function aside from its name, and we can gather the information then via BTF and trace that information effectively.
All right. That is the last of those talks. We actually are going to come back and do some more talks about portable eBPF programming, XRP storage in the kernel, and a couple other great ones. But we're coming into a break, so we're going to take about a 10-minute break. Get up, stretch, get something to drink, have a snack, be prepared for the last few talks that we have for the day. And again, thank you so much for all of the great participation that we've seen today. So thank you so much.
We are back from break. Look at that. Now, first, before we go through the last little bit of our lightning talks, we only have 2 more. We're almost at the end, people, so stay with me. I want to show you all something. Someone took us up on our offer to show their watch party. So I want to throw that on the screen. Isn't that amazing? Thank you, Shivam. I appreciate it. You have been so supportive. If you all look closely, you can see the bees on the right monitor. Like, that is dedication. Thank you so much. So now we're going to go to the first of our last 2 talks. It is going to be, and if you all can make fun of me on Slack or in Twitter, I don't mind, because it took me a minute to realize this wasn't Iter, it's Iter. Thank you, Liz. So we're going to have Cgroup Iter, a step toward container-oriented observability, and that's going to be from Hal.
A typical BPF observability tool has 2 functionalities. One is to collect the CPU system-wide data and store them in a map, and the second is to export the data to the users. BPF observability tool is designed mainly for system administrators. This is inevitable because using BPF requires privileges. So what we see is that BPF observability tools are used by privileged users who collect system-wide data and selectively export the data to unprivileged users. However, the requirement of privileges poses obstacles for container-based workloads to use BPF. Container-based computing is a modern computing paradigm that runs workloads in isolated environment called containers. These workloads running in containers do not have a privilege, therefore cannot leverage the flexibility of BPF to gain observability. One of the solutions is for them to talk to a privileged daemon and gather stats from the daemon. But this adds a runtime overhead. It would really be great to introduce BPF for containerized workloads to use. The missing piece here is that the lack of a fine-grained permission control for BPF observability. With that question, let's take a close look at the containers. Container is a technology built on 2 key kernel features, namespace and a Cgroup. Cgroup is a technique that achieves resource management for container workloads in Linux kernel. Cgroup, short for control group, serves the purpose of limit, account for, and isolate the resource usages for a collection of processes. In order to achieve hierarchical resource management, Cgroups are organized in a hierarchical manner, specifically in a tree. It would be great to use BPF for Cgroup-based resource control and accounting. In fact, there are already recent developments that uses BPF for resource control in networking. What I'm going to talk about today is the other direction, that is using BPF for Cgroup-based observability. There is a type of a BPF program called a BTFGen Iter that allows users to supply a program to iterate and process a collection of objects in the kernel. There have many types of objects that can be iterated using BPF Iter. Using BPF Iter, one can iterate through kernel symbols, or iterate through existing tasks in the system, or iterating sockets in the system, etc. And the users can customize the processing logic for each object encountered during the iteration. BPF Iter is a great tool for observability. As you can already guess from the title of my talk, what I'm going to talk about today is an iterator for Cgroups. Cgroup Iter iterates a Cgroup subtree and allows users to supply a program to process the Cgroups in that subtree. The Cgroup Iter program defines what data to export to user space and in what format, Cgroup Iter is often paired with another BPF program whose job is to collect data and store data in the map. This program can be a tracing program, but not necessarily. It doesn't have to, it's not limited to tracing. Cgroup Iter's job is just for controlling data exportation and organizes the data based on Cgroups. I put a small example here to demonstrate Cgroup Iter. In this example, I'm assuming in this example, we have a Cgroup Iter program. You can see that we assume that there are already some data stored in a map, stats map here. And what the Cgroup Iter program does is to get the data out of the map and then print the data to the user. What I want to clarify here is that Cgroup Iter is not only limited to data exportation. It could also be used for any type of Cgroup-based processing. After loaded into the kernel, a Cgroup Iter program needs to attach to a Cgroup. That Cgroup is the beginning of the iteration. The Cgroup can be specified using a file descriptor or a Cgroup ID. Using file descriptor allows Cgroup Iter to be used for Cgroup v1, but Cgroup ID works for Cgroup v2. So Cgroup Iter is compatible with both Cgroup v1 and v2. Usually, we will have a control plane that loads and attaches the BPF programs. During attaching, the control plane needs to specify the order of the iteration as the parameter for the attachment for Cgroup Iter. Currently, there are 4 orders to be supported, and one can choose from for iteration: pre-order, post-order, and target Cgroup only, and walking up the ancestors. The pre-order and the post-orders are used for iterating descendants. Using pre-order, one can implement propagating commands down from the root to descendant Cgroups. Using post-order, one can implement aggregate data from descendant Cgroups. The third mode, target Cgroup only or self-only, asks the Cgroup iterator to process only one Cgroup, that is, the target Cgroup. And in this case, the Cgroup Iter degenerates into a trivial form that is only processing a single Cgroup. Cgroup Iter can also walk up ancestors. When walking up ancestors, it provides a safety guarantee that the walking will not escape the reader's namespace, so that the Cgroups outside of the namespace won't be visible by the readers in the container. When attaching a Cgroup Iter program, a BPF link will be generated. A BPF link is a kernel object, much like a BPF map or BPF program. One can ping the map in BPF file system, and this will create a file in the file system. The pinged link could be read. Upon read, the Cgroup Iter program will be triggered and prints out the content based on what the program indicates. Reading the stats as a file is pretty powerful. It has basically 2 implications. First, the file could be served as a flexible BPF-based extension to the Cgroup file system. We could reconstruct the Cgroup hierarchy in BPF file system and transform Cgroup Iter as an extensible interface to export any information associated with a Cgroup or a Cgroup subtree. Second, we could rely on the file system's permission model to control the permission for accessing the data exported by Cgroup Iter. Exporting as a file allows us to read the stats, to set the stats to be readable, writable, or only accessible by a specific group of users, because files could be set so. The file interface is a more fine-grained model than the BPF map read syscall interface. With Cgroup Iter, we can now safely allow workloads running in the containers to read the container stats without the help of a privilege daemon. That's the end goal of Cgroup Iter. I call this container-oriented observability. The following steps can be performed by a control plan to give observability to workloads in the containers. The control plan first needs to prepare BPF programs by loading them into the kernel. The BPF program will include the one that collects the stats and also the Cgroup Iter one to export the stats. Then the control plan needs to attach the Cgroup Iter program to the target Cgroup. That could be the root Cgroup of the container. And then it could ping the generated link generated from attachment to the BPF file system. Then it needs to adjust the permission of the pinged link and map the link into the container. By doing so, the observability is controlled by the control plan, and the control plan has a full control on what is allowed to read and what isn't by using BPF programs. Processes inside the container won't be able to read the Cgroups outside its namespace, as this is restricted by the kernel. There are several advantages of using Cgroup Iters. The first one is that it achieves daemonness. The control plan does not need to be involved when the workload could read the stats, because the stats could be exported as files. It simply reads a file prepared by the control plan, and the privileged control plan is not needed. It's not needed at read time. It's only needed at the Cgroup creation time and deletion time, that is for mapping the stats files into the container. And it's also secure because the readers cannot escape its container. It could not read the Cgroups outside of its namespace. It's also flexible because the control plan can define what is allowed to be read by the workloads in the container just by providing the necessary BPF Cgroup Iter programs. And last, it's also compatible with the Cgroup v1 and v2. So this is pretty nice. So when we were developing Cgroup Iter kernel features, we included an example as a self-test to demonstrate the use case of Cgroup Iter. The provided tests consists of two parts. One is the set of BPF programs that is responsible for collecting some memory Cgroup stats, and the other is a Cgroup Iter that dump the stats. And the other part is the control plan that demonstrates that is just some scaffolding that's necessary for connecting everything together. It includes loading the program, attach the program, ping the program, etc. This example pretty much resembles the real use cases that I can imagine. To summarize my talk, Cgroup Iter is a new BPF feature that is recently made available in the kernel. Its end goal is to enable a wide use of BPF in containerized workloads. At its very early stage, I'm welcome any feedbacks, comments, or suggestions. I really hope that it will inspire more applications that use BPF in containerized computing. Like I said, Cgroup Iter is potentially very powerful. It's not just dumping stats, but it could also be used for many types of processes. It's beyond imagination. That concludes my talk. Thank you.
you for that wonderful talk. And also, I fibbed. There now are 2 more talks left. The next one will be BTFGen, one step closer to our truly portable eBPF programs, from Mauricio and Rafael.
Hello everybody, welcome to this presentation about BTFGen. I'm Mauricio, I work as a software engineer at Microsoft, and I will do this presentation together with Rafael, that is an open source engineer at Aqua Security. Okay, so let's get started. The problem that we are trying to solve with this presentation, or better with this BTFGen project, is about eBPF portability. We all know that the eBPF is a virtual machine that runs inside the Linux kernel. So we could think that this is possible to just compile our eBPF program and run that in different Linux machines without any problem. But if you are a little bit familiar with eBPF, you know that this is not easy to do, because those eBPF programs need to access different kernel structures to get information that is used for tracing or security purposes in general. The problem here is that the layout of those kernel structures is not stable. So it could happen that from one version to the other, the name of a member inside a structure is changed. It could happen that there is a new member introduced at the beginning of the structure, and there are many different cases where the layout of a kernel structure from one version to another could change. Even worse, if we are running the same kernel version, it could happen that we compile the kernel with different configuration flags, and in this case, the layout of those structures is also different. For instance, here we have a very simple BPF program. In this case, we are accessing the PID of the task structure, and when we look at the definition of that structure, we can see that just at the beginning, there is a conditional compilation flag. So according to the value of this flag, the position of the PID member within the structure is going to change. So what it means is that if we compile an eBPF program for a machine that doesn't have this enabled, that eBPF program is not going to work in a machine that has this flag enabled, because the position of this member is going to be different, and then our eBPF program is going to read the information on a run position in memory. There is already a solution for this problem. This is called compile once, run everywhere. This has been around since 2018. And this is a mechanism to patch the BPF programs at runtime. So the idea is that we compile the BPF program a single time, and we ship the compile eBPF program. And then on each target machine where we want to run the program, there is a loader library that takes some information about the types of the kernel in a format that is called BTF. More about that in a second. And by using that information, the loader library is able to adjust the instructions on the BPF program to read the members at the right position. All of this is based on something that is called BTF. This stands for BPF type format, and this is a metadata that describes the different kernel types. This is an information that is generated when we compile the kernel, and this is exposed to the loader library and in general to the users by using this file. This is important to notice here that this is only available when the kernel was compiled by using this configuration flag. Here we can look at a small piece of BTF. So I only want to look at the definition of the task structure. So if we run that command, we can get some information. For instance, we see that there is a structure that is called task structure. We get some information about the size of the structure. This is the number of members, and then we get information for each of the members present on that structure. Here we have the member that we are interested in. This is the PID member, and this is the piece that is interesting for us. So we get information about what is the offset of that member within the structure. So this is the information that the loader library uses to perform the patching of the BPF program. Right, so far everything is great. By using core, we are able to compile our program in one machine, and we are able to ship that program and run on different machines, and the program is patched before running on those machines. But what is the problem? That this BTF information that is needed by the loader library in order to perform the relocations is not available on all the kernels. So maybe this flag is not enabled, or maybe this is running on an older kernel that even doesn't have this flag available. The good news is that for most of the new versions of the major distributions, this is now enabled. So users that are running a very new kernel version are all good. There are no problems there, but in this work, we were concentrating in users that are running older versions, and for some specific reasons, they can't update to more recent versions of the Linux kernel. So what can we do with those older kernels, right? This is still possible to get the BTF information for those. For instance, there is a project that was created by Rafael and by the Aqua Security folks that is called BTF Hub that stores BTF files for different Linux kernel distributions, for different versions of Linux distributions. This is some information that is generated by taking some of the debug packages provided by those distributions, and yeah, we can go to a GitHub repository and we can fetch the file that we need. So the idea there is that all of this is the same, the loader library is just the same, but we have to put some logic somewhere to take the BTF file from BTF Hub, to download that and to install that into the system. So according to the kernel version that we are running, we take the file, install that in our system, and then we provide that to the loader library, and this can do the work just the same as before. Well, what are the limitations with this approach? Each file is around 5 megabytes big. So what it means for us is that this is not possible to ship a lot of those files together with our EBPF program, because it will require a lot of storage. So for instance, for supporting 1000 kernels, we will need something like 5 gigabytes. Of course, this is not feasible. So the alternative there is to download that file from internet at runtime, but of course this is not ideal because we need some time to download the file, and even worse, in many cases this is not possible to reach an external host to download that file. This is where BTFGen comes into play. So what happens is that in order to perform the relocations, we don't need information about all the types of the kernel. So usually when we write an eBPF program, this eBPF program is accessing some of the members of those structures. We are not trying to access all the members in a given eBPF program. So in order to perform the relocation, we only need the information about the types that our eBPF program is using. So the idea behind BTFGen is to take a full BTF file with all the types of the kernel, describing all the types of the kernel, to take different BPF objects, and then by using BTFGen we are able to generate smaller versions of those BTF files that only contain the types that we need in order to perform the relocation for those programs. So for instance here, as I mentioned before, the source BTF file is around 5 megabytes. We have the information about all the types there, and the generated file, according to the complexity of the BPF programs, could be some kilobytes long. So the advantage in this case is that we can ship those generated files together with our application. So for instance, in some experiments that we did for BCC supporting all something like 1000 kernels only require few megabytes, few extra megabytes. So in this case, this is possible to put the BTF information for many different kernel versions together with our application. So what happens in that case is that at runtime, again, according to our Linux distribution architecture and kernel version that we are running, we extract the specific BTF file for that environment, and we give this to the loader library that performs the patching process as before. And that's it from my side. So I give the word to Rafael that is going to present you a demonstration of how it works.
Thank you, Mauricio. So the idea here is to show one of the projects benefiting from what Mauricio just described. We have like 3 or 4 projects using BTF Hub together with BTFGen. The 2 biggest projects are Microsoft's Inspector Gadget, and Tracy from Aqua Security. Using Tracy as an example, we have the BTF Hub archive in here, and it contains, like Mauricio said, a bunch of BTF files, one to each kernel we would like to support, remembering that these kernel versions here don't have embedded BTF files on them. So that's why we have external BTF files. And then checking how we are compiling tracing and using it. The idea is very simple. Every time we generate eBPF object that supports core and is meant to be portable, we also embed a bunch of BTF files in the final binary. So in our case, it's a Golang binary. And what we're doing is that we are embedding all the BTF files that we have generated with BTFGen in the same binary. And then during execution, we're going to use them, as I'm going to show you in a bit. The scripts that do this are basically getting all the files from BTF Hub, and to each of those files, we uncompress the full BTFs, and then we run BPF2, gen, min, core BTF, and then we have a full BTF file, and then the file that we're about to generate, and the eBPF object we just compiled. So during the compilation, you're going to see something like this, which is basically running BPF2 and then generating a custom BTF file from this full BTF file for this eBPF object. And if we pick this file is the full 4 or 5 megabyte file, and this one is a very, very small file that is going to be embedded in our final application. And the make file has one option called BTF Hub equals to 1, which will embed all the BTF files that we would like to support. And it works a little bit like this. So it compiles the BPF core object. And right after compiling the BPF core object, it synchronizes and it brings all the BTFs I would like to support for all the kernel versions and their architectures I would like to have supported, right? And right after bringing those files, I pick and start generating the smaller BTF files for the object we currently have. So as you can see here, we are supporting Red Hat 8, the versions that did not have BTF file included on it. And then we're supporting a bunch of Ubuntu or Oracle 8 kernels, Ubuntu kernels. And what each line here means is that for each of those BTF files, we are calculating a smaller BTF file base for this object, right? And at the end, if we go to the end, we finally generate the full Golang binary containing all those BTF files embedded on them, right? Like this directive here. Okay, and as you can see, for example, in a kernel that does have all the BTF file, all the BTF information available, you can simply do a paho to this file in here, and you're going to see all the types that your current kernel supports, right? And it's a very long file, right? But when we go to a machine that doesn't have that file available, like for example, an Ubuntu Falco with a kernel 5.4.0-91, this kernel did not have BTF embedded information available. So what we will see now is that if I execute Tracy, it has that available information embedded on it. So it generates a temporary file. And this BTF file here is the BTF file for this kernel, but only the portion needed for running this program, the BPF, the core object for Tracy. So if I do a paho in that file, instead of having all the types available to the kernel, it has only the types needed by the EBPF object we're currently running. So as you can see here, it's a small file and it's not complete as well. So it's not as big as the full kernel types, and it has only the types and the fields needed for the BPF program we're currently running. Right, and with that, I give you back the speech. Thank you, Mauricio.
Thank you, Rafael. So in the conclusion, we have that BTFGen can be used to support core on kernels that don't provide BTF information. And yeah, we want to be clear here. We know that BTFGen is a temporal solution. So once all the users upgrade the kernels to versions that provide this BTF information, BTFGen won't be needed anymore. But in the meanwhile, we can use that to fill that gap. And finally, those are two blog posts in case you want to know more. The first one describes the implementation of BTFGen, gives a general overview, and also goes into some of the details. And in the second one, explains how this is used by Tracy to solve the lack of BTF information. That's it. Thank you.
All right. Thank you for that lovely talk. And thank you for providing learning material at the end. That is very helpful. We are officially at our last talk. You all, please continue to ask questions like you've been doing so wonderfully today. And our last talk is XRP, In-Kernel Storage Functions with eBPF from Yuhang.
Hello, my name is Yu Hongzhong. I'm a first-year PhD student in computer science at Columbia University. Today, I'm going to talk about our work, XRP, In-Kernel Storage Function with eBPF. This is a paper we published at a system conference, OSDI 2022. With new storage technologies, storage devices are getting much faster. As a result, kernel software is becoming a bottleneck for storage. Let's take a look at the breakdown of the average latency of a random 512-byte read, which shows the percentage of time spent on hardware and kernel software with different type of disk. Here, kernel software means the storage stack inside the kernel. We can see that a higher percentage of time is spent on kernel software when the storage device is faster. Kernel software overhead accounts for around 50% of read latency on the second generation of Optane SSD. So what is the kernel software overhead? Let's take a look at the data path of one typical read request. When the application submits a read request, they first need to cross the kernel boundary and reach the syscall layer. After that, the request will be sent to the file system and the block layer, and is then forwarded to the NVMe driver. The NVMe driver then sends the request to the storage device. Once the read request is completed, the response is returned to user space in reverse order. Here, the percentage of time spent in storage device represents the hardware overhead, and the rest are the kernel software overhead. Okay, now we know the composition of the kernel software overhead, but the question is how to eliminate this overhead. One extreme way to do that is to bypass the kernel entirely. Kernel bypass is a popular topic in academia. There are many exciting work such as Demi-kernel, Shenango, and Snap, which build kernel bypass system for storage or network applications. In industry, the most common library for storage kernel bypass is SPDK. Kernel bypass configures the storage device to be managed by user space and disables its interrupt. The user space application can then communicate with the storage device directly without using any syscall. By eliminating all of the kernel software overhead, the read latency can be reduced by up to 49%. However, kernel bypass is not a panacea. It is true that it does not incur the overhead of the kernel storage stack, but using kernel bypass also means that there is no fine-grained access control because any process can access the device directly. What makes it worse is that it requires busy polling for completion, since the interrupt of the storage device is disabled. That means processes cannot use CPU when waiting for I/O. It has two further implications. First, CPU cycles are wasted when I/O utilization is low. Also, CPU cannot be shared efficiently among multiple processes. Okay, kernel bypass doesn't fit the need for people who need isolation and want to use CPU more efficiently. Since isolation and resource scheduling are two key services provided by the kernel, the question then becomes how to reduce the kernel software overhead without bypassing the kernel. Notice that the NVMe driver itself only accounts for 1.8% of the read latency. If the application can offload an EBPF function into the NVMe driver to submit read request and process read response, then we can potentially reduce the read latency by up to 47%, which is very close to the speedup achieved by the kernel bypass approach. Let's look at an example to see how offloading eBPF function into the kernel can reduce the kernel software overhead. Many popular key-value stores use B plus tree as their index data structure. Without eBPF functions, a B plus tree index lookup consists of issuing multiple IO requests to traverse the B plus tree from the user space. Initially, we are at the read point. We need to issue the first read request to fetch the read return disk. The read request needs to traverse the entire kernel software stack to reach the storage device, and the data needs to be sent back to user space. The application would then parse the data to determine whether we arrive at the leaf node. If not, we will extract the offset of the next node to fetch. Since we haven't reached a leaf node yet, the application will issue another read request to fetch the next node. The new read request will traverse the entire kernel software stack again, and the response will be returned to user space. The application will parse that node again and finds that this is still not a leaf node. Therefore, a new read request will be issued to fetch one of the children of the current node. The new read request follows the same data path. And finally, when parsing the data, the application finds that this is a leaf node and can finish the lookup. Here, we see that node parsing and IO request submission are performed in user space, which means we traverse the full kernel software stack multiple times. Now we show how offloading eBPF function into the kernel can help B plus tree index lookup. Assume that the application can offload an eBPF function to the NVMe driver. We still start from the root node and issue the first read request to fetch the root node. The first request will cross the kernel boundary and traverse the submission path of the entire kernel software stack. However, when the first read request is completed, instead of return the data all the way back to user space, we can call the eBPF function right at the NVMe driver. The eBPF function will parse the data and submit the next read request directly to the storage device. This is also the case for the second request. When the third request is completed, the eBPF function finds that this is a leaf node and returns the leaf node to user space. Here, we only traverse the full kernel software stack once and reduce the latency of intermediate I/O by up to 47%. We call a sequence of such I/O requests as a chain of dependent read requests. We find that chain of dependent read requests are very common in storage applications. B tree and LSM tree, including their variants, are used as the index in most of the storage engines. They both issue dependent read requests to perform lookups. Therefore, we want to build a framework for storage engines to accelerate dependent read requests using in-kernel function. To achieve this goal, we built XRP, a framework for in-kernel storage function with eBPF. XRP allows application to offload eBPF functions into the kernel. When the application initiates a chain of read requests, The eBPF function can then be called to parse IO response and submit more requests if necessary. Only the final result will be returned to user space. We can use XRP to accelerate many different types of operations, such as index lookup, range queries, and aggregations. eBPF is already widely used in networking. For example, it can be used for packet filtering, packet forwarding, packet tracing, and network scheduling. In these networking use cases, an eBPF program can operate on each packet independently. However, on the contrary, a storage eBPF program needs to traverse a large index data structure in a stateful way. This is not an easy problem. XRP is the first system that adopts eBPF to reduce the kernel software overstack for storage. To adopt eBPF in storage, we address the following research challenges. Since this is a short presentation, I'm not going to cover the solution to all these challenges. Instead, I will show how to write a storage eBPF program in XRP. Here, we present a simple eBPF program for B+tree index lookup. The eBPF program is to parse the tree node fetched from disk and submit the next request until it reaches a leaf node. A context is passed to the eBPF program as the parameter. It has the pointer of two buffers. The data buffer stores the data that was fetched from disk, and the scratch buffer is provided as a private scratch space for the user space application and the eBPF program. The scratch buffer can be used to store lookup parameter or intermediate state. The kernel will never touch the scratch buffer. The data buffer contains the B+tree node that is going to be parsed. The search key is stored in the scratch buffer by the user space application so that it can be used by the eBPF program. The function first checks the type of the current tree node. If this is a leaf node, it can return the result to user space without submitting more IO requests. Otherwise, this is an internal node, and the function needs to search for the next node to fetch. The fanout field records the number of children in the current node. We can linearly search all the pivots to find the next node. Here, max fanout is used to ensure that this for loop is always bounded. Without it, this program will be rejected by the eBPF verifier. After finding the child node in need, the eBPF program extracts its address from the current node and specifies the next request in the eBPF context. This is just a very simple example. In fact, BPF can traverse many types of data structures. We integrate XRP with two key-value stores. The first one is BTFGen, a simple B+tree key-value store we built to take advantage of fast storage devices and XRP. It allows us to test the performance limit of XRP. We also integrate XRP with WildTiger's LSM tree. WildTiger is a popular key-value store and is part of MongoDB. By integrating XRP with WildTiger, we show that XRP can accelerate the production key-value store in YCSP workloads. To see how well XRP works, we evaluate it in different ways. Due to the time limit, I will focus on the first two questions in the evaluation. What is the performance benefit of XRP? How does XRP compare to kernel bypass? You can find the answer to the other questions in our OSDI paper. To study the performance benefit of XRP, let's look at the multi-threaded throughput in BTFGen with uniform random 512-byte read. The x-axis is the number of threads, and y-axis is the throughput. Note that we use 6 CPU cores for the evaluation, which is shown by the vertical gray dashed line. Compared to read syscall, XRP, where the number of threads does not exceed the head of the kernel storage stack. However, SPDK failed to scale beyond 6 threads because SPDK. We can also see We can also see that XRP can scale well, even if the number of threads exceeds the number of cores. This is because XRP alleviates the CPU contention by reducing the CPU overhead per IO request. To see how XRP compared to kernel bypass, the performance of SPDK is added to the throughput graph. Here, this multi-threaded experiment approximates a multi-tenant environment where each thread represents a different storage application running on the same machine. We see that when the number of threads does not exceed the number of cores, SPDK always achieves a better throughput, since it doesn't incur the overhead of the kernel storage stack. However, SPDK failed to scale beyond 6 threads because SPDK threads cannot yield CPU when waiting for I/O to complete. To sum up, XRP provides performance that is close to or even better than SPDK without sacrificing isolation and CPU efficiency. We also measure the tail latency in the multi-threaded experiment. The x-axis is again the number of threads, and the y-axis is the 99.9% tail latency. The green dashed line shows the number of CPU cores. Similar to the throughput result, compared to using read syscall, XRP improved tail latency of BPF-KV by up to 45%. We can also see that tail latency of SPDK spiked to around 10 milliseconds when the number of threads is greater than the number of cores by more than 50%. In summary, XRP is the first system to use eBPF to accelerate common storage applications. Also, XRP captures most of the performance benefits of kernel bypass without sacrificing CPU utilization and access control. XRP is an open source academic research project. You can find more details in our paper. If you have any question, you can reach me by email. Thanks.
I think one of the rootkits in these demos tried to just take us out at the end of this thing, and I don't appreciate that. Anyway, that was a great talk. I appreciate you highlighting the B tree while you were exploring XRP. So now, I want to go back to one of my community watch parties. Before I share the bingo bee locations, Jeff Spalletta decided to let us know he has a Chromecast-enabled work-from-home watch party. Thank you so much, and you have been so interactive this entire time. I really appreciate it. All right, let's do some bee stuff, people. Let's see if I know how to handle this remote and stuff at the end of the day. Let's go. So, first off, you were supposed to find all 9 bees scattered throughout the event. So let's see what you all did, okay? You ready? So this was your beekeeper bee. This was your astronaut bee. Security bee. Electrician bee. You already had Tetra bee, my favorite little bee dude. Jedi bee. Skiing bee. Detective bee. And the last bee would have been virtual bee. So let me show you where you should have seen these. I hope someone was actually able to complete their card. All right, so the next one would have been on agenda day 1. And you will have found the bee up in the right corner. The next one would have been the Zurich watch party slide. There's that bee, Skeevy. I think that was appropriate. The next one, oh, let me tell you something. This one absolutely was my favorite one because it got a couple of people here in the office. So here we go. That was the astronaut bee. And you probably couldn't tell because that's the bee that should have been there. And this is what astronaut bee looks like. This is my favorite one, actually. All right, agenda day 2. So I call this the day 2B because you could have gotten this B on this slide, or you could have gotten this B on this slide. And let's see where the next ones were. We also had the programming and internal slide. You would have found that B up in the corner. And on this slide, you would have gotten the beekeeper bee. We're not through yet. COCB, which was security bee. I did that one. That was the stop sign. I thought that was cute. We also had the capture the flag Jedi bee. I also thought that was appropriate. And the official agenda day 2 slide had this bee. So that was the final bee. I hope you all, or someone at least, successfully completed your beekeeping duties. I believe Liz is in the Slack channel right now asking if anyone was able to complete bingo. So if you did complete bingo, make sure to share your card. Again, if you completed it, you probably get a prize. So that was bingo. I have enjoyed that one. Let's bring Duffy back in so we can say goodbye together.
Yay!
The hat
Awesome.
is back. Hello, Duffy.
The hat is back. I kind of go back and forth, you know, sometimes it gets too long.
Guess what? We survived. Like, we survived the whole thing, and they tried to take us out at the end.
Let's see if let's try something super
Hold
awkward.
on, wait. I actually did it right the first time. Wait. Here we go.
Almost there. There we go.
Yeah. Oh, wait. Okay. This is not working. I ate too much food. There we go.
Anyway, what an incredible event. So much information shared. So much. I mean, I think I saw a comment earlier about how the lightning talks were happening fast enough that like a lightning talk would happen and the person was like processing the data that they had just received from the talk.
And then we'd be on the next
the other
one.
talk had started and it was like, it was just coming too fast, you know. I'm grateful that that all of these talks will be available after the show. And remember that you can go back to our schedule, ebpf.io/summit-2022. And from there, just as though you would like try and see more information about one of the talks, if you click on one of those talks, you will then see the slides that were uploaded, and soon you will see a link to the video that will be uploaded.
I'm just going to be real with you.
So that's how you can. Yeah.
We're going to say the next couple of days.
Yeah.
Don't fuss at us if it takes us a week. You see how things in technology go. You know it may be a little bit of a delay. Just work with us, okay? But we're going to get those up as quickly as possible.
And most of all, I think, you know, both of us want to thank all of you, both the presenters and the speakers and everybody who participated in the chat. Thank you all so much for being a part of this and making it such a great event.
This has been enjoyable. And would you believe this is the first time I actually got to meet Duffy in person?
That's true. Yeah.
Yeah.
And one of the things, one of the hidden secrets about this particular situation, I'm not sure if you mentioned this, but the shot behind you is one that you took.
Oh yeah, I took this over the weekend. Because this is my first time here, and I was able to take that shot. And I promise you, as soon as I get back, I'm making this my a background or something, because I loved it. It was so peaceful, you all. But this has been the culmination of a very good. I will say this, and I say this to Liz, and I say this to Duffy, and I say this to Bill, who you all have not seen, but you may know whether you know him or not. Being a new person on this team has culminated in a very good EBPF summit because I just got to meet my entire team for the first time. So,
yay!
Yeah. So I have really enjoyed myself, and the community and the Slack, people in Slack have really made this enjoyable. So thank you. And the AV guys, thank you. Because, honey, y'all have a job. All right. Duffy, you got anything else?
The last thing I'm going to say is that we're coming up on KubeCon happening at the end of October in Detroit. And at that event, we will be doing an EBPF day. So if you're coming to that event, make sure you check that out. Every week we do Echo office hours. This week on Friday, that's tomorrow, we will play a video that Liz and I recorded today, time travel, where we will actually be going through a live solve of CTF Challenge 3. So definitely check that out if you're having trouble. And everything else I have to say is all there. Yeah.
Oh, wait.
Thank you all
and
so
if
much.
you all have any, yeah. Oh, wait, before we cut off. As far as Echo is concerned, you all may see me every once in a while. That notwithstanding, we have a repo for Echo. If you have ideas, place them in our Echo repo or place them in Slack, and we will try our best to explore the topics that you share with us. Okay, now I'm through.
All right.
All right.
Thank you, everyone.
Thanks, everybody. Bye.